You think you're sitting still right now. I mean, it feels like you are, right? Every part of you, from the solid chair beneath you to the calm air in the room, is sending the same message to your brain. You are at rest. But here's the thing. It's all an illusion. Welcome to the science for deep sleep. If this kind of calm exploration into the universe helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether near an ocean, a forest, a city, or somewhere quiet in between, feel free to share where you're watching or listening from. It might just be the greatest, most convincing trick the universe has ever played. Because in the time it takes me to say this sentence, you, this planet, and everything you hold dear has blasted thousands of miles through the dark of space. That's not a metaphor. It's a physical fact. You might feel perfectly still, but you're actually a passenger on a cosmic voyage, hurtling through space at over 500,000 miles per hour. So, how is this possible? And why on earth can't you feel a thing? To figure that out, we need to unravel the beautiful, cosmic illusion of stillness. We're going on a journey, layer by layer, from where you're sitting right now to the edge of the entire observable universe. We're going to prove that from the tiniest, jiggling atom to the most massive, lumbering galaxy, everything is in a state of constant, unstoppable motion. To understand why you can't feel this unbelievable speed, we don't have to look to the stars. We just have to think about something a little closer to home, an airplane. Think about the takeoff. It's a jolt. You feel the raw power of the engines pressing you into your seat as the world outside blurs. That feeling is acceleration asterisk a change in your speed, and our bodies are experts at detecting it. But then, the plane hits its cruising altitude and speed, and everything changes. The engine's roar fades to a hum. The pressure in your seat is gone. You can unbuckle, get up, and walk down the aisle just as if you were on solid ground. If you drop a pen, it falls straight down. Inside this metal tube, flying at 600 miles per hour, miles above the ground, it feels like you're standing still. Why? Because everything inside the plane, the seats, the air, the pen, is all moving together at the same, constant speed. Physicists have a name for this: an inertial frame of reference. When you're inside one, without looking out a window, it's impossible to tell you're moving. This is the first crucial piece of the puzzle. Your brain didn't evolve to detect constant speed. It evolved to detect changes in speed like a sudden stumble or a pouncing predator. Smooth, constant motion gets filtered out. It becomes the new, still. So that feeling of stillness you have right now? Think of it like this. You're just inside a much, much bigger airplane. The first layer. A planet in a pirouette. Let's start peeling back the layers of motion, beginning with the ground right under your feet. Planet Earth is not a static stage, it's a spinning top of unimaginable size. Right now, our planet is performing a constant, graceful pirouette. And the speed is anything but trivial. If you're at the equator, you're being carried eastward at about 1,040 miles per hour. Roughly 1,670 kilometers per hour. That's faster than the speed of sound. Even in a mid-latitude city like New York or Tokyo, you're still moving at a brisk 800 to 900 miles per hour. Okay, so why aren't we all being flung off into space? It's the airplane principle, just on a planetary scale. You, the buildings, the oceans, and maybe most importantly the entire blanket of air around us are all spinning together at the exact same constant speed. There's number 1,000 mile per hour gale force wind because the wind is moving with you. Gravity does the rest, holding everything firmly to the surface, easily overpowering the forces trying to throw you outward. But even if you can't feel it, the clues are everywhere. The most obvious is the cycle of day and night. The sun doesn't really rise and set, our horizon just turns to face it and then turns away. More subtle clues exist, too. The Coriolis effect, which causes hurricanes to spin in different directions in the northern and southern hemispheres, is a ghostly fingerprint of this planetary motion. So, Layer 1. You're on a spinning ball, moving at the speed of a jet. But believe it or not, this is by far the slowest part of our entire journey. The second layer, our annual cosmic lap. Now, let's zoom out. Way out, past the atmosphere. You'd see that Earth's spin is just one of its two main movements. Our planet isn't just spinning in place. It's on a massive journey around our star, the Sun. This is the second layer of your motion, Earth's orbit. The scale of this journey is just mind-boggling. The path is over 584 million miles long, 940 million kilometers. To travel that far in 1 year, Earth has to move unbelievably fast. And it does. Right now, your speed from this orbit alone is about 67,000 miles per hour, around 107,000 kilometers per hour. To put that in perspective, a high-powered rifle bullet travels at maybe 2,000 miles per hour. You are moving more than 30 times faster. In the few seconds it took to read that, you've traveled hundreds of miles. And again, you feel absolutely nothing. The airplane principle is back. We are all passengers on spaceship Earth, and our velocity, while enormous, is incredibly constant. Gravity acts as a smooth, steady tether, keeping us on this cosmic ride without any bumps or jolts to alert our senses. So now we have two motions stacked. You're on a planet spinning like a top, while that whole top is hurtling around the Sun. Your actual path through space isn't a simple circle, it's a spiral, a corkscrew through the void. But this cosmic dance is just getting started. The entire solar system is on an even bigger journey. The third layer, a starship called Sol. For centuries, we imagined the Sun as the fixed, unmoving anchor at the center of everything. But the Sun is not an anchor. It's just one star among billions, and it's moving, too. And this is where the speeds get, well, astronomical. Our entire solar system, the Sun, the planets, you, me, everything is in a grand orbit around the center of our home galaxy, the Milky Way. Deep in the galaxy's core, about 26,000 light-years away, is a supermassive black hole called Sagittarius A*, whose immense gravity commands the orbits of hundreds of billions of stars, our Sun included. Our speed in this galactic orbit is staggering. An average of 514,000 miles per hour. About 828,000 kilometers per hour. At this speed, you could fly around the Earth's equator in under 3 minutes. This is the motion that dwarfs all the others. One full lap, a galactic year, takes about 225 to 250 million years to complete. The last time our solar system was in this part of the galaxy, the first dinosaurs were just beginning to show up. Humans have existed for only a tiny fraction of a single one of these laps. Again, why don't we feel it? Because everything is coming along for the ride. The Sun, the Earth, the other planets, we are all falling together around the galactic center in one gigantic reference frame. The nearest stars are all making similar journeys, so relative to them, we barely seem to move at all. You aren't just sitting in a chair. You are in the command seat of a planet, which is docked on a starship called Sol, cruising at over 500,000 miles per hour on a voyage that lasts hundreds of millions of years. But all this talk of motion begs a deeper question. Motion. Relative to what? The physics of motion. A duel of giants. That question, relative to what, sparked one of the biggest debates in science, pitting two titans of physics against each other. On one side was Sir Isaac Newton. For his laws of motion to work, he needed a universal stage where everything happened. He called it absolute space, an invisible, unmovable, infinite grid that was the ultimate frame of reference. He argued that an object's true motion was its speed relative to this absolute grid. To prove it, he came up with a famous thought experiment, the rotating bucket. Imagine hanging a bucket of water from a rope. At first, the water is still and its surface is flat. Then you spin the bucket. Initially, the bucket moves but the water doesn't, yet the surface is still flat. But as friction gets the water spinning with the bucket, its surface becomes a deep curve. Newton asked why. Since the water and bucket are now moving together, he said the curve must be caused by the water accelerating relative to absolute space itself. On the other side were thinkers like Ernst Mach. They argued that absolute space was meaningless. Motion is just the relationship between objects. Mach had a different take on the bucket. What if the water's surface curves because it's rotating relative to every other object in the entire universe, all the distant stars and galaxies? This debate was a stalemate for centuries. The tiebreaker came from an experiment designed to finally find Newton's absolute space. In 1887, Albert Michelson and Edward Morley set out to detect the ether wind, a theoretical medium that light was thought to travel through. They built a super-sensitive device to measure differences in the speed of light beams traveling in different directions, expecting Earth's motion through the ether to affect them. They ran the experiment, rotated it, and ran it again. And they found absolutely nothing. No matter how they pointed their machine, the speed of light was stubbornly, frustratingly, the same. This glorious failure was the first strong evidence that there was no ether, no absolute space for us to move through. That result was a bombshell. Physics was in chaos. Einstein's revolution, tearing up the rulebook. The chaos lasted until a young patent clerk named Albert Einstein came along and basically tore up the old rulebook. In 1905, he published his theory of special relativity, built on two revolutionary ideas. First, the laws of physics are the same for everyone in uniform motion. This takes our airplane analogy and applies it to the whole universe. There is no special place or true state of rest. Second, the speed of light in a vacuum is the same for all observers. This boldly accepted the result of the Michelson-Morley experiment as a fact. Put those two ideas together, and Newton's universe just falls apart. No absolute space. No absolute rest. Motion is always relative. The question, how fast am I moving, has no answer until you finish the sentence. Relative to the ground? Relative to the sun? Relative to the galaxy? Each one has a different, but equally correct, answer. But Einstein wasn't done. A decade later, his theory of general relativity revealed that gravity isn't a force pulling us, but a curve in the fabric of spacetime. The Earth isn't being pulled by the sun. It's just following the straightest possible path through the curved spacetime created by the sun's huge mass. Einstein's theories gave us a universe with no anchor and no center, where speed and position are all a matter of perspective. There is no ultimate state of rest to measure against. There's only the dynamic dance of matter and energy. But even that isn't the whole story. Because it turns out that the very fabric of space itself is on the move. The final zoom out, the expanding canvas. There is one last, all-encompassing layer of motion. Our Milky Way galaxy is part of a cluster of galaxies called the local group. And our whole group is being pulled toward the giant Virgo cluster of galaxies. But this cosmic tug-of-war is happening on an expanding canvas. In the 1920s, Edwin Hubble discovered that distant galaxies are all moving away from us. This isn't motion through space, but the expansion asterisk of space itself. The fabric of spacetime is stretching, carrying the galaxies along with it like raisins in a rising loaf of bread. This expansion gives us one final, cosmic reference frame to measure against. The cosmic microwave background, or CMB. It's the faint, leftover heat from the Big Bang that fills the entire universe. This ancient light is almost perfectly uniform, but not quite. In one direction it's a tiny bit warmer, blue shifted, and in the opposite direction it's a tiny bit cooler, red shifted. This is a Doppler shift caused by our motion relative to it. By measuring this shift, we can calculate our total combined speed. Our solar system is moving at about 828,000 miles per hour, or 370 kilometers per second, relative to the cosmic microwave background. Our entire Milky Way galaxy is moving at about 552 kilometers per second relative to the CMB. So, is this it? Is the CMB the universe's absolute rest? Not quite. It's a convenient cosmic average, but it's not physically special. The laws of physics work the same within it as any other frame. There is no center to this expansion, no ultimate finish line. From the smallest vibration of an atom to the stretching of spacetime itself, the universe is defined by motion. True stillness isn't just impossible. It's a concept that has no place in reality. So let's come back. All the way back. Past the receding galaxies, past our Milky Way's 230 million year orbit, past our Sun, back to our spinning, spiraling Earth. Back to your room. Back to your chair. You feel still. But now you know the secret. That stillness is a beautiful and profound illusion, a trick of perception that hides the most fundamental truth of your existence. You are on an incredible journey. You aren't just watching the universe from the sidelines. You are a participant. You are stardust, assembled on a spinning rock, which is hurtling through a spiral galaxy that's surfing across an expanding universe. The reality you inhabit is one of perpetual, unstoppable change. Motion is the default state of everything. So the next time you have a quiet moment, the next time you feel perfectly, deeply still, smile. Acknowledge the magnificent deception. And enjoy the ride. If this cosmic trip expanded your perspective, consider subscribing for more journeys into the nature of reality. And a question for the comments. What part of this universal dance surprised you the most? The sheer speed of our galaxy? The idea that stillness is just a concept? Let us know below. Why we don't fly off a spinning Earth. Right now, you are hurtling through space at about 1,000 miles per hour. That's faster than the speed of sound, faster than most fighter jets. Every second of every day, you're riding a cosmic carousel that's spinning at a mind-boggling velocity. So, why don't you feel it? And more importantly, why aren't you, your house, your dog, and everything else being flung off the planet and into the cold, dark void of space? This is one of the most profound and yet simple questions in all of science. It's a paradox that puzzled our ancestors for millennia. They looked up and saw the sun, moon, and stars wheeling overhead in a majestic, daily parade. The most logical conclusion was that the heavens were moving and the earth was the firm, unmoving center of everything, suggesting the ground beneath their feet was actually in a state of perpetual, high-speed motion would have sounded like madness. And yet, that's the reality. We're living on a planetary-sized centrifuge, and the only thing standing between us and an unscheduled trip into orbit is a set of powerful, invisible forces. This explanation uncovers those forces, gravity and constant motion, that keep us all firmly, and thankfully, planted on the ground. Unraveling this mystery is a journey through the fundamental laws of physics. It's a trip that will take us from a smooth airplane ride to the very center of the Earth, and from the heart of a hurricane to the silent dance of the galaxies. By the end, you won't just understand why you feel perfectly still right now, but you'll also gain a new appreciation for the intricate physics that make life on a spinning planet possible. The answer is a beautiful conspiracy of physical laws, all working in perfect harmony. The illusion of stillness, understanding constant motion. The first piece of the puzzle, the reason we don't feel this incredible speed, can be summed up in two words: constant motion. To be a bit more formal, uniform velocity. Our bodies, as sensitive as they are, aren't built to detect speed. They're built to detect changes in speed. That change is called acceleration. To get a feel for this, let's use a relatable analogy. Being in an airplane. Imagine you're sitting on the runway. As the plane starts to move, you feel it immediately. A powerful force pushes you back into your seat. This is acceleration. Your body is going from zero to a very high velocity. You feel every bump on the tarmac, every little change in speed. Then, the plane takes off. It's a period of intense acceleration as the engines push this massive metal tube into the sky. Your inner ear is sending frantic signals to your brain. We're moving fast, and we're changing direction. But then, something magical happens. The plane reaches its cruising altitude of 35,000 feet. The engines throttle back to a steady hum. The captain announces you've reached a cruising speed of 500 miles per hour. A flight attendant comes by and pours you a cup of coffee. And here's the crucial part. The coffee falls straight down into the cup. It doesn't fly to the back of the plane. If you close your eyes, you could almost convince yourself you're perfectly still. You feel no sensation of movement at all. Why? Because everything is moving together. You, the coffee cup, the air in the cabin, you're all moving as one cohesive system at a constant 500 miles per hour. Because your velocity isn't changing, there's no acceleration to feel. Your brain registers this state of constant, uniform motion as being identical to being at rest. This gets at a huge idea in physics, something Galileo Galilei figured out hundreds of years ago: the principle of inertia. He imagined being in the cabin of a ship on a perfectly smooth sea. He noted that a dropped ball would fall straight to your feet, just as it would on land. You would have no way of knowing you were in motion unless you looked out the window. The Earth is our giant, planetary ship, sailing through an incredibly smooth cosmic sea. The speed of its rotation is astonishingly constant. So, just like on the airplane, you aren't moving on the Earth, you're moving with it. The ground, the building you're in, and even the air you're breathing are all spinning together at the same constant speed, about 1,040 miles per hour at the equator. Because you're moving in perfect sync with your surroundings, there is no relative motion to detect. There's no wind rushing past you because the atmosphere is spinning along with you. Your brain, just like in the airplane cabin, interprets this state of perfect, uniform motion as complete stillness. You'd only feel the spin if it changed. If the Earth were to suddenly speed up or slow down, you would feel it in the most dramatic way imaginable. This explains why we don't feel the motion. But it doesn't answer the second, bigger question. If we're spinning so fast, why don't we get flung off? The answer to that lies in a cosmic battle of forces, one that is happening to you right now. The invisible tether, gravity versus the outward push. So, we don't feel the Earth's spin because it's incredibly smooth. But we are still moving in a giant circle. And anyone who's been on a spinning merry-go-round knows that moving in a circle creates a powerful outward push. This is the effect of inertia. Your body wants to go in a straight line, but the ride forces you to turn. We call that feeling centrifugal force. The Earth's rotation absolutely creates this effect. Your body wants to travel in a straight line out into space, but the spinning Earth constantly forces you along its circular path. This creates a very real, though small, outward acceleration. So, this becomes a battle of forces. On one side, the outward push from the spin tries to fling us off. On the other side is the force that keeps us here: gravity. Let's be clear. Gravity is the undisputed, heavyweight champion of this fight. It's not even a fair contest. Gravity is the fundamental force of attraction between any two objects that have mass. The more massive an object, the stronger its pull. And the Earth is, to put it mildly, unbelievably massive. This enormous mass generates a powerful gravitational field, constantly pulling everything toward its center. This is the invisible tether that gives you weight and anchors you, the oceans, and the atmosphere to the surface. Now, let's look at the challenger. The outward push from the spin, or centripetal acceleration. At the equator, where the rotational speed is fastest, this outward acceleration is at its maximum. But even there, it's only about 0.034 meters per second squared. Compare that to the acceleration from gravity, which pulls you down at about 9.8 meters per second squared. This means the force of gravity is roughly 290 times stronger than the outward push from the spin. It's a cosmic tug of war where one team has 290 people and the other has one. Gravity wins. Easily. This is why you don't fly off into space. The invisible tether of gravity is vastly more powerful than the tiny push generated by the planet's rotation. However, the outward push does have a small, measurable effect. It counteracts gravity just enough to make you slightly lighter at the equator than you would be at the poles. There are two reasons for this. First, the outward push is strongest at the equator and zero at the poles. Second, the Earth isn't a perfect sphere. The spin has caused it to bulge slightly at the middle over billions of years. This means if you're at the equator, you're actually about 13 miles further from the Earth's center than if you were at a pole. Combine these two factors, and an object at the equator will weigh about 0.5% less than it does at the poles. If you weighed 200 pounds at the North Pole, you'd weigh about 199 pounds at the equator. It's a real difference, but far too small for anyone to notice. So, the second part of the mystery is solved. We aren't flung off the Earth because gravity is holding us down with immense force. The outward push is real, but it's so weak in comparison that its only noticeable effect is making you weigh a tiny bit less at the equator. But to truly appreciate these forces, let's ask the most dramatic question of all. What if the Earth suddenly stopped spinning? The what if scenario. The apocalypse of a sudden stop. We've established why we don't feel the Earth's spin. A perfect balance of constant motion and overpowering gravity. But to really grasp the forces at play, let's break the system. What would happen if, in an instant, the Earth just stopped? The result would be, without exaggeration, the single most cataclysmic event in the planet's history. An apocalypse of physics. First, remember inertia. An object in motion stays in motion. Right now, everything on the surface, people, animals, trees, buildings, even the oceans, is moving eastward at a tremendous speed. Over 1,000 mph at the equator. If the solid Earth suddenly stopped, everything on top of it would not. Imagine being in a car going 60 miles per hour when it hits a brick wall. The car stops. You don't. You fly forward until something stops you. Now scale that up to a planetary level. The moment the Earth stopped, every person, building, and boulder would become a projectile, launched eastward at hundreds of miles per hour. The entire surface of the planet would be instantly scoured clean by a force of unimaginable violence. But that's just the beginning. The atmosphere is also spinning. If the ground stopped, the air wouldn't. We'd be hit with global winds of over 1,000 miles per hour, generating supersonic shockwaves that would obliterate anything left standing. The friction would likely ignite global firestorms. Then, there are the oceans. Their inertia would send them surging eastward, creating tsunamis not measured in feet, but in miles. Entire oceans would slosh out of their basins, scouring continents down to bedrock. The planet itself would be reshaped. The spin causes the Earth to bulge at the equator. Without it, gravity would pull the Earth back into a perfect sphere. The water that had just inundated the continents would retreat toward the poles, creating a single megacontinent around the equator and two vast polar oceans. And it gets worse. The day-night cycle would end. One side of the Earth would face the sun for 6 months, baking into a lifeless desert. The other side would be plunged into a frozen, 6-month night. The temperature difference would create winds of unimaginable power. Finally, we could lose our protective magnetic field. Scientists believe the field is generated by the motion of molten iron in the Earth's core, which is tied to the planet's rotation. Without it, deadly solar wind and cosmic radiation would strip away our atmosphere over time, leaving Earth a barren, airless rock, much like Mars. This terrifying scenario vividly illustrates the sheer power of the forces that are in perfect, silent balance right now. We're riding a tiger, but because we're moving with the tiger and a powerful gravitational leash keeps us in the saddle, we don't notice the speed. This thought experiment is a stark reminder of what would happen if that tiger ever stopped. The wow facts, deeper clues to a spinning world. While we can't feel the Earth's rotation, its fingerprints are everywhere, from our weather to the path of a long-range bullet. These are the wow facts that prove the Earth is spinning. Let's start with one of the most elegant proofs ever devised: the Foucault pendulum. In 1851, French physicist Léon Foucault had a brilliant idea. He knew that a freely swinging pendulum would keep swinging in the same fixed plane. He reasoned that if the Earth rotated beneath it, the pendulum's swing would appear to change direction to an observer on the ground. To test this, he suspended a 62-pound iron ball from a 220-foot wire inside the Panthéon in Paris, inviting the scientific community with a note: "You are invited to see the Earth turn." As the pendulum swung, a pointer on the bottom traced lines in sand. Just as he predicted, the lines shifted slightly with each swing. But here's the beautiful part: the pendulum wasn't changing direction. It was faithfully swinging in the same plane relative to the stars. The Earth, the floor of the Panthéon, and everyone watching were slowly rotating counterclockwise underneath it. It was the first direct, mechanical proof of the Earth's rotation, so clear anyone could see it. The second major fingerprint of the spin is the Coriolis effect. It's the same principle as the pendulum, but applied to things moving freely across the Earth, like air and water. Imagine you're at the North Pole and you throw a ball to a friend on the equator. As the ball travels south, the Earth rotates eastward beneath it. From your perspective, it would look like a mysterious force is deflecting the ball to the right. This apparent deflection is the Coriolis effect. In the northern hemisphere, it pushes moving objects to the right, and in the southern hemisphere, to the left. The effect is negligible over short distances. It does not affect the water draining in your sink. That's a myth. But over vast distances, it is the master architect of our planet's weather. When air rushes toward a low-pressure zone in the northern hemisphere, the Coriolis effect deflects it to the right, causing the entire system to spin counterclockwise. This is how hurricanes are born. This is also why hurricanes almost never form near the equator. The Coriolis force is too weak there to get the spin started. Even the military has to account for it. For long-range artillery or sniper shots, the deflection from the Earth's rotation is significant enough that it must be calculated to hit the target. These clues are all around us. The very shape of our planet, every storm, and every ocean current is a dance with the physics of a rotating world, proof that we are in constant motion. Beyond rotation, the cosmic zoom out. Our journey doesn't end with Earth's spin. That dizzying rotation is only the first layer of a much grander cosmic dance. So, let's zoom out. You'll see our spinning globe is also orbiting the Sun at a staggering speed of about 67,000 miles per hour. In the time it took you to read that sentence, you traveled hundreds of miles through space. And yet, you feel nothing. Why? The same reason you don't feel the spin. This orbital motion is incredibly constant. We're in a state of continuous freefall around the Sun, and just like astronauts in orbit who feel weightless, we feel no sensation of this incredible speed. But why stop there? Zoom out even further. Our entire solar system is just one part of the Milky Way galaxy. And just as the Earth orbits the Sun, our Sun orbits the supermassive black hole at the center of our galaxy. The speed of this journey is even more mind-blowing. About 500,000 miles per hour. Even at that pace, the galaxy is so immense that it takes our solar system between 225 and 250 million years to complete a single orbit, a galactic year. The last time our solar system was in this spot, dinosaurs were just beginning to roam the Earth. Surely, we must be done now? The galaxy itself is the final, unmoving reference point, right? Wrong. Zoom out one last time. Our galaxy is part of a cluster called the local group, and this entire group is being pulled by gravity toward a massive concentration of matter known as the Great Attractor. Relative to the cosmic microwave background, the faint afterglow of the Big Bang, our galaxy is moving at a truly stupefying 1.3 million miles per hour, about 600 kilometers per second. So let's recap. You're sitting on a planet spinning at 1,000 mph. That planet is orbiting a star at 67,000 mph. That star is orbiting a galactic center at 500,000 mph. And that whole galaxy is hurtling through the universe at 1.3 million miles per hour. And through all these layers of nested, ever faster motion, you can sit back, sip some coffee, and feel perfectly, peacefully still. It's the ultimate testament to the principle of constant motion. Nothing in the universe truly stands still. We are just along for the ride. The question of why we don't fly off a spinning Earth takes us on a tour of the most fundamental principles of our universe. The answer comes down to two big ideas working in perfect concert. First, the principle of constant motion. We don't feel the Earth's speed because we, the atmosphere, and everything around us are moving together as one seamless system. Our bodies only feel changes in speed, and the Earth's spin is astonishingly smooth. Second, the raw, overwhelming power of gravity. While the spin creates a tiny outward push, it's hopelessly outmatched by our planet's immense gravitational pull. Gravity is the invisible tether that's nearly 300 times stronger than the force trying to fling us away. We've seen that while we can't feel this motion, we can see its fingerprints everywhere in the graceful arc of a Foucault pendulum, the spiral arms of a hurricane, and the very shape of our planet. And we've zoomed out to see that our motion is a complex dance of orbits within orbits, a multi-layered rush through the cosmos. So the next time you stand outside, take a moment to appreciate the profound physics of your situation. You're not standing still. You're a passenger on a cosmic vessel of unimaginable speed, held fast by an invisible force, moving in perfect, silent unison with the world around you. You are hurtling through the universe, and the reason you don't feel a thing is the most elegant magic trick in all of physics. If this journey through the physics of our spinning planet blew your mind, make sure to hit that subscribe button and ring the notification bell so you don't miss our next deep dive. We've talked about what would happen if the Earth stopped spinning, but what other cosmic, what if, scenarios do you find fascinating? Let me know in the comments below. I read all of them, and your idea might just spark the next video. The sun's insane orbit we're trapped in. Right now, you probably feel pretty still. Maybe you're sitting down, maybe you're lying in bed, but you feel the solid, unmoving ground beneath you. It's a feeling of stability. But that feeling of stillness? It's the greatest illusion you'll ever experience. In reality, you are on a cosmic road trip at a speed that defies all human intuition. Right now, you're hurtling through the galaxy at over 515,000 miles per hour, or about 828,000 kilometers per hour. You didn't choose to get on this ride. There are no stops and no exits. You can never get off. Because the vehicle you're strapped into isn't a car or a plane. It's the Earth. And the Earth is being relentlessly dragged by our Sun on an insane, billion-year orbit around the violent, chaotic heart of the Milky Way galaxy. This isn't science fiction. It's your reality. We tend to think of the sun as this fixed point, the motionless center of everything, with all the planets obediently circling it. But the sun is anything but stationary. It's a traveler, caught in a gravitational dance on a scale that's almost impossible to wrap your head around. Its path isn't a simple circle. It's a wild, wavy, and unimaginably long journey that carries you and everything you've ever known along with it. Today, we're going to peel back that comfortable illusion of stillness and reveal the true nature of the cosmic orbit you're inescapably a part of. We'll uncover the mind-bending speeds, the eons-long timeline, the invisible forces that dictate our path, and the beautiful, complex, helical motion our world traces as it spirals through the void. This is the story of the sun's insane orbit, and by the end, you'll never look at your place in the universe the same way again. This isn't just a story about a star. It's the story of your never-ending journey through the cosmos. The familiar anchor. Before we blast off on this grand galactic tour, let's ground ourselves in what we all learned in school. The solar system. It's a model of beautiful, clockwork-like predictability. At the center is the sun, a colossal sphere of plasma that makes up 86% of all the mass in the entire solar system. It's the undisputed gravitational king. Around it, in neat, flat orbits, are the planets. We live on the third one, Earth, which diligently completes its loop around the sun every 365 days. This is what gives us our seasons. To do this, we travel at a brisk 67,000 miles per hour, or about 107,000 kilometers per hour. It's a speed that already feels unreal, but we don't notice it because everything, the atmosphere, the oceans, the ground, is moving right along with us. Further out, you have Mars, which takes about 2 Earth years for its lap. Then comes the giant, Jupiter, which takes nearly 12 years to make one orbit. And then there's Saturn with its iconic rings, Uranus, and distant Neptune, which takes a staggering 165 Earth years for a single trip around our star. The whole system is a masterpiece of gravitational balance, a cosmic family portrait that seems stable and self-contained. This is our home base. This is the "you are here" map we're all comfortable with. For centuries, this was the extent of our cosmic vision. We saw the sun as the ultimate anchor, the unmoving foundation of our existence. The stars beyond were just a glittering, fixed wallpaper for our local drama. But this comforting picture is just the first, tiny piece of a much larger, much more dynamic puzzle. It's like describing a single car on a massive highway without ever mentioning the highway itself, or the fact that the car is moving at incredible speed. To understand our true motion, we have to zoom out. Not just past Neptune, but far beyond, into the sprawling expanse of the Milky Way. It's only from this perspective that the anchor of our solar system reveals itself for what it truly is. A tiny vessel on an endless voyage. The zoom out and revelation. Okay, let's do it. Let's zoom out. We pull back from our familiar solar system, and the neat paths of the planets shrink until they're just glittering threads. The sun itself diminishes into a single point of light. As we keep pulling back, millions, then billions of other stars come into view. We are now looking at our home galaxy, the Milky Way. It's a breathtaking spiral, a celestial city containing hundreds of billions of stars, stretching over 100,000 light-years across. And our sun isn't at the center. We live in a relatively quiet, suburban neighborhood, in a smaller spiral arm called the Orion Spur, about 27,000 light-years from the brilliant, chaotic galactic core. And here is the grand revelation. Nothing in this city stands still. The entire galaxy is a swirling, dynamic system. And our sun is caught right in the current. The sun, our anchor, is on an immense orbit of its own, circling the center of the Milky Way galaxy. This isn't a gentle drift. It's a frantic race through space. Our best measurements show that the Sun, and our entire solar system with it, is traveling at an average speed of about 828,000 kilometers per hour, which is roughly 515,000 miles per hour. Let's put that into perspective. A commercial jet flies at about 550 miles per hour. Our solar system is moving nearly 1,000 times faster than that. Even the Parker Solar Probe, the fastest spacecraft humanity has ever built, only reaches about 430,000 miles per hour at its closest approach to the Sun. We are moving faster than that, all the time, every single day. In the time it took you to read that last sentence, you've traveled thousands of miles through the galaxy. Think of the Milky Way as a giant cosmic carousel. The billions of stars are the horses, all circling a brilliant central pillar. Our Sun is just one of those horses, and we are all passengers on its back. Every star you see in the night sky is also on this ride. But because they are so incredibly far away, their movement relative to us is almost impossible to see over a human lifespan, creating the illusion of a static, unchanging backdrop. But it's an illusion. We are not just orbiting the Sun. We are being dragged by the Sun on this much grander, much faster journey. Every year, when the Earth completes one lap around the Sun, we don't return to the same spot in the galaxy. The entire racetrack has moved. By your next birthday, you will be hundreds of millions of miles away from where you are in the galaxy right now. There's no going back. We are trapped on this celestial highway, forever moving forward into new, uncharted regions of the Milky Way. The scale and the timeline. We've established the mind-boggling speed of our journey. But to truly grasp the insanity of this orbit, we need to talk about its scale, the sheer time it takes to complete one single lap. The time it takes for the Sun to orbit the center of the Milky Way is called a galactic year, or a cosmic year. And one galactic year is approximately 230 million Earth years. Let that sink in. 230 million years. All of recorded human history, from the first cave paintings to the device you're using right now, is just a microscopic sliver of one galactic year. It represents about 0.004% of a single orbit. We are born, live, and die in what amounts to a cosmic instant, while our solar system barely budges along its path. To make this meaningful, we have to leave human history behind and turn to our planet's geological timescale. The Earth is about 4.5 billion years old. Using our 230 million year orbit, we can calculate that our planet has been around for about 20 galactic years. In its entire lifetime, Earth has made this grand circuit only about 20 times. So, what was happening on Earth 1 galactic year ago? The last time our solar system was in this exact region of the Milky Way, it was the late Triassic period. The very first dinosaurs were just beginning to appear. Creatures like Eoraptor and Herrerasaurus, small two-legged predators, were taking their first evolutionary steps. The continents were fused together into the supercontinent Pangaea, and there were no flowering plants anywhere on Earth. That was our galactic neighborhood, 1 cosmic year ago. Let's jump forward in the orbit. About half a galactic year ago, roughly 115 million years back, we were on the opposite side of the galaxy. It was the heart of the Cretaceous period, and the age of dinosaurs was in full swing. Giant sauropods, the largest land animals to ever live, roamed the Earth. Tyrannosaurus rex and Triceratops hadn't even evolved yet. The rise and fall of the most dominant creatures in our planet's history took place over the course of a single lap around the Milky Way. Entire geological eras, the shifting of continents, the evolution and extinction of countless species, these are the milestones we pass on this journey. You are on a vessel that has witnessed the entirety of life's drama on Earth as it cycles again and again through the starry expanse. The why? The unseen forces. So what's driving all this? What force could possibly keep our Sun, a star a million times the volume of Earth, tethered in such a vast orbit? The answer lies in two of the most mysterious and powerful things in our universe: a supermassive black hole and an enigmatic substance called dark matter. Let's start with the main anchor. At the very heart of the Milky Way, about 27,000 light-years away, lies a monster named Sagittarius A, pronounced Sagittarius A star. It's a supermassive black hole with a mass around 3 million times that of our own Sun, all compressed into a region of space smaller than the orbit of Mercury. This is the gravitational center of our galaxy. Just as the Earth orbits the Sun, our Sun is in a stable orbit around this supermassive black hole. It's constantly being pulled towards the galactic center, but its colossal sideways velocity that 515,000 miles per hour keeps it from ever being swallowed. It's forever falling, and forever missing. But there's a twist. When astronomers measured our galaxy's rotation, they found something that shouldn't be possible. Stars far from the center should orbit more slowly, just like Neptune orbits the Sun much more slowly than Mercury. But that's not what we see. Stars on the outer edges of the galaxy are moving just as fast as stars much closer to the middle. This is a cosmic crime scene. If the only mass was the stuff we can see, stars, gas, dust, then these fast-moving outer stars should be flung off into deep space. The galaxy should be tearing itself apart. And yet, it isn't. This leads to a profound conclusion. There must be a huge amount of extra mass we can't see. This invisible substance doesn't shine or reflect light. We can only detect it by its gravity. Scientists gave it a fittingly mysterious name: dark matter. Dark matter is thought to form a vast, spherical halo that surrounds the entire visible disk of the Milky Way, providing the extra gravitational glue needed to hold our rapidly spinning galaxy together. In fact, dark matter is estimated to make up about 85% of all matter in the universe. The stars, the planets, you and me, were all just the visible fluff embedded within this enormous, invisible scaffold. So, our Sun isn't just being pulled by the black hole at the center. It's also surfing through this immense halo of dark matter, whose gravity keeps its velocity high and its orbit stable. The nature of the path. So we have the speed, the timeline, and the forces. But what does the path actually look like? A flat circle is far too simple. The true journey is much more elegant. A three-dimensional dance through space, involving a gentle, wave-like bobbing motion in a mesmerizing corkscrew pattern traced by the planets. First, the Sun doesn't stay perfectly flat within the Milky Way's disk. As it orbits, it also bobs up and down, like a horse on a carousel. It passes through the dense central plane of the galaxy, moves above it, gets pulled back down, passes through again, and moves below. This up and down cycle is caused by the gravitational pull of all the stars and gas concentrated in the galactic disk. This whole oscillation takes about 60 to 70 million years to complete. Right now, our solar system is about 50 light-years above the galactic midplane and still moving away from it. But here's the most visually stunning part. As the Sun moves forward on this wavy path, the planets are still orbiting around it. The combination of these two motions creates a breathtaking visual. The planets don't trace flat circles, they trace out helices. They form a cosmic corkscrew. Imagine the Sun as the tip of a bullet flying through space. The Earth, in its yearly orbit, is like a point on the side of that bullet, spiraling around it as it moves forward. Our planet is literally corkscrewing its way through the galaxy. This is the image that shatters the old 2D textbook diagrams. It transforms our view of the planets from predictable marbles on a table into dynamic travelers on a vortex-like path. This is the true poetry of our motion. We are living on a planet that is spinning on its axis, revolving around the Sun, and spiraling through the galaxy as part of a grand, helical procession. We aren't just passengers on a road trip. We are performers in a cosmic ballet. The philosophical return. We've journeyed across unimaginable distances and timescales, wrestled with mind-bending speeds, and met the unseen forces that govern our path. Now, it's time to bring this cosmic perspective back home. Because this isn't just an astronomy lecture. This is your personal story. It all leads to one powerful realization. You are a traveler on spaceship Earth, a passenger on an ancient and ongoing cosmic voyage. The atoms that make up your body, the carbon, the nitrogen, the oxygen, were forged in the hearts of long-dead stars. That stardust has been on this journey for billions of years, completing the circuit around the Milky Way many times. Now, for a brief moment in eternity, those atoms have assembled to become you. And you are still on that journey. When you feel the stillness of the room around you, remember the 515,000 mile per hour reality. You are being carried on a celestial current that flows through the spiral arms of the Milky Way. This journey connects you to everything. The light from distant stars comes from fellow travelers on this same galactic carousel. The supermassive black hole at the center is the anchor providing the stability for your existence. The invisible dark matter surrounding us is the silent guardian that keeps our cosmic home from flying apart. This knowledge doesn't make us small. It makes us part of the grandest story of all. To be alive is to be in motion. We are born from stardust and carried on a galactic wind. We live our lives on a spiraling world that was on this same road trip for billions of years before we existed, and will continue for billions more after we're gone. There's a profound connection that comes from this. You are a momentary consciousness that has woken up on the deck of a starship, mid-voyage. You didn't see the beginning and you won't see the end. But for this one precious moment, you get to look out the window and marvel at the view. We've learned that the comfortable stillness we feel is an illusion. We are passengers on a planet that is spinning, orbiting, and spiraling through the galaxy at over 800,000 kilometers per hour. We've discovered that this journey is so long that one lap takes around 230 million years, a timescale measured by the rise and fall of the dinosaurs. We now know our path is dictated by the gravity of a supermassive black hole and an even larger, invisible halo of dark matter. And we've seen the beautiful, hidden truth of our motion. Not a flat circle, but a wavy, helical dance through the stars. You are not standing still. You are, and have always been, a galactic traveler. The next time you look up at the sun, remember what it truly is. Not a fixed anchor, but the powerful engine of your personal starship, pulling you on the most insane, inescapable, and magnificent road trip the universe has to offer. If this cosmic journey blew your mind, make sure you subscribe and hit the notification bell. We explore the biggest questions in the cosmos every week, and you won't want to miss where we're going next. Thank you for traveling with us today. We're being pulled towards something we can't see. The feeling of stillness is the greatest illusion you'll ever experience. You might be sitting in a chair, feeling perfectly still. But you are not. Not even close. Right now, you, this planet, and our entire galaxy are being violently pulled across the universe at over 1,000,000 miles per hour. For decades, astronomers were baffled. They called the source of this pull the Great Attractor. Now, they're finally piecing together the truth, and it's a cosmic detective story grander and stranger than we ever imagined. We are not just drifting, we are being summoned. The question is, by what? The illusion of stillness. To understand the violent pull on our galaxy, we first have to appreciate the layers of motion we're already caught in. We have to peel back the illusion of stillness, layer by dizzying layer. Let's start with the ground beneath your feet. It feels solid, unmoving. Yet, it's attached to a planet that's spinning on its axis. Depending on your latitude, your speed is somewhere around 1,000 miles per hour at the equator, faster than a commercial jetliner. A constant, silent velocity you have never once felt. But that's just the first circle in a dizzying cosmic dance. This spinning Earth is also locked in orbit around the Sun. To keep from either flying off into the void or falling into our star, our entire world is moving at an astonishing 67,000 miles per hour. That's nearly 30 kilometers every single second. You feel nothing. And even that journey is dwarfed by the next. Our entire solar system is just one of countless star systems orbiting the supermassive black hole at the heart of our Milky Way galaxy. This is a journey of almost unimaginable scale. Our solar system is careening through the galaxy at roughly 500,000 miles per hour. To complete just one of these galactic orbits takes our Sun about 230 million years. Think about that. The last time our solar system was in this exact spot, the first dinosaurs were just beginning to walk the Earth. The entirety of human history has taken place in a tiny fraction of a single galactic year. For a long time, this was the complete picture. Earth spins. Earth orbits the Sun. The Sun orbits the galaxy. A neat, nested system. But that's not the end of the story. Because when astronomers developed the tools to look beyond our own galaxy to measure the motion of the Milky Way itself, they found something deeply unsettling. Our galaxy, this entire spinning city of stars, was not just moving in its own neat orbit. It was being pulled. All of it. With a ferocious velocity that nothing could explain. The illusion of stillness was shattered, not just for our planet, but for our entire corner of the universe. We weren't just on a carousel, we were on a runaway train, hurtling towards a destination unknown. The cosmic rulebook, and how we break it. To understand just how strange this is, you first have to know the fundamental rule of the universe. Everything is moving away from everything else. It's called the Hubble-Lemaitre law. The classic analogy is to imagine the universe as a balloon with dots drawn on it. As you inflate the balloon, every dot moves away from every other dot. The very fabric of space is expanding, carrying all the galaxies with it. This is the Hubble flow, the default motion of the cosmos. So, how do you get an objective sense of motion when everything is moving? You need a fixed backdrop. Miraculously, the universe has one. The cosmic microwave background, or the CMB. The CMB is the oldest light in the universe, the faint afterglow of the Big Bang itself. It's incredibly uniform, coming from every direction in the sky. This makes it the ultimate reference frame, the closest thing to a stationary background the universe has to offer. If we are moving, the CMB should appear slightly hotter and bluer in the direction we're heading, and slightly cooler and redder in the direction we're moving away from. When scientists pointed their telescopes at the sky, they found exactly that. They detected a cosmic dipole. And this is where the mystery truly begins. The data showed that our solar system, our entire Milky Way galaxy, our neighbor Andromeda, and all the other galaxies in our local group, are all screaming across the universe at roughly 630 kilometers per second. That's about 4 million miles per hour. This was not the gentle drift of the Hubble flow. This was a directed, violent motion asterisk on top of the universal expansion. Something was dragging us through the water. We are being pulled towards a specific point in the sky, in the direction of the constellations Leo and Virgo. This peculiar velocity tells us the universe isn't a perfectly smooth, inflating balloon. It has texture. It has gravity. And somewhere out there, in the darkness, there is a concentration of mass so enormous that its gravitational influence is reaching across hundreds of millions of light years to grab our galaxy and thousands of others. The hunt for what astronomers would ominously name the Great Attractor had begun. The investigation, cosmic detectives. The discovery in the 1970s was like finding a single, giant footprint. It was proof that something huge was out there, but what? To find the culprit, astronomers had to become cosmic detectives, piecing together a trail of gravitational evidence, galaxy by galaxy. This monumental task was taken up in the 1980s by a team famously known as the Seven Samurai. They reasoned that if the Milky Way was being pulled, then other nearby galaxies should be, too. By mapping these motions, they could trace the gravitational currents back to their source. The challenge was immense. To figure out a galaxy's true motion, you need to know its true distance. The Seven Samurai pioneered the use of a clever trick for spiral galaxies. It's a relationship that links a galaxy's brightness to its rotation speed. A faster spinning galaxy is more massive, and therefore brighter. By measuring how fast a galaxy spun, they could figure out how bright it truly was, and from there, its distance. For years, they meticulously observed hundreds of galaxies. As they compiled their data, a stunning picture emerged. It wasn't just our little group of galaxies that was in motion. Vast collections of galaxies, stretching across more than 100 million light-years, were all streaming in the same direction. They called this phenomenon bulk flow. It was a breathtaking confirmation. Our peculiar velocity was not an anomaly. We were part of a massive cosmic migration, a river of galaxies all flowing towards a common gravitational center. The data pointed to a region of space about 150 to 250 million light-years away, in the direction of the constellations Centaurus and Hydra. The evidence was overwhelming. There had to be an incredible concentration of mass there. The team estimated that to exert such a powerful pull, this unseen thing must have a mass equivalent to tens of thousands of Milky Way galaxies. The footprint wasn't just from a giant, it was from a titan. The mystery had a location, and a name that captured its terrifying grandeur: the Great Attractor. But identifying the location of a suspect is one thing. Getting a clear look is another. And when astronomers pointed their telescopes to find it, they were met with a frustrating, almost impenetrable wall. The prime suspect was hiding. The prime suspect, hiding in plain sight. With a name like the Great Attractor, you can't help but picture a cosmic monster. A term that comes to mind is cosmic horror light, a perfect blend of scientific awe and existential dread. The initial estimates of its pull were equivalent to 1,000,000 billion suns. Astronomers envisioned it as a colossal gravitational well, a deep depression in the fabric of spacetime. Our galaxy wasn't so much being pulled as it was flowing downhill into this massive basin. But when they tried to observe this region, they ran into a major obstacle: the zone of avoidance. This isn't a physical place, but a zone our telescopes try to avoid. It's the plane of our own Milky Way galaxy. Looking toward the Great Attractor means looking through the densest part of our own galaxy, a thick band of stars, gas, and dust that acts like a celestial fog, blocking the light from whatever lies beyond. It's like trying to spot a ship on the horizon while standing in a blizzard. To peer through this galactic smog, astronomers had to turn to other wavelengths of light, like radio waves and X-rays, which can penetrate the dust. And peeking through the fog, they found it. A large supercluster of galaxies, the Norma Cluster, situated right in the heart of the Great Attractor region. For a time, this seemed to be the answer. The Great Attractor was the Norma Cluster, a massive congregation of galaxies whose combined gravity was reeling us in. Case closed. But as more data came in, a nagging problem emerged. The math didn't add up. When astronomers calculated the mass of the Norma Cluster and all the other visible galaxies, they found it was significant, but not nearly significant enough. The observed mass could only account for a fraction of the gravitational pull needed to explain our 1.4 million mph velocity. The prime suspect was in the right place, but it wasn't powerful enough to commit the crime on its own. The mystery, far from being solved, had just deepened. If the Norma Cluster wasn't the sole culprit, then something else was out there. Something even bigger. The plot twist. A conspiracy of gravity. The realization that the Great Attractor wasn't massive enough was a classic plot twist. It meant the detectives had been focusing on the henchman, while the real mastermind was still lurking in the shadows. To find it, they had to cast their nets even wider. And when they did, they found something that utterly dwarfed the Great Attractor. Located about 650 million light-years away, far beyond the Great Attractor, lay an even more stupendous collection of galaxies. The Shapley Supercluster. This structure is the largest and most massive concentration of galaxies in our local universe. It's a true cosmic behemoth, containing over 8,000 galaxies with a mass of at least 10 quadrillion suns. That's many times the estimated mass of the Great Attractor region. Suddenly, the picture changed. The Great Attractor is like a nearby valley, its gravity creating a local dip that shapes our path. But the Shapley Supercluster is the towering mountain range on the horizon behind it. Our velocity is the result of being pulled downhill towards the Great Attractor, while that entire landscape is itself tilting towards the colossal mass of Shapley. The Great Attractor is no longer the destination, it's a waypoint on a much longer journey. This discovery led to an even more beautiful concept. In 2014, a team of astronomers led by R. Brent Tully redefined our entire cosmic address. They mapped the paths of over 100,000 galaxies, identifying a vast basin of attraction where all the galaxies, including our own, are flowing inwards. This cosmic watershed, our home supercluster, was given the Hawaiian name Laniakea, meaning immense heaven. Laniakea is a staggering structure, spanning over 520 million light-years and containing the mass of 100 quadrillion suns. The Milky Way and everything we once thought of as our local universe are all just minor parts of this single, gravitationally bound entity. And what lies at the gravitational heart of Laniakea, the point where all its streams converge? The Great Attractor. This is the beautiful resolution to the mystery. Our peculiar velocity is simply our motion within Laniakea. The Great Attractor isn't some monster pulling us from the outside, it is the center of our own home. But Laniakea itself, this entire immense structure, is on the move, dominated by the even greater pull of the distant Shapley Supercluster. We live in a river of galaxies called Laniakea, and that entire river is flowing towards an ocean called Shapley. The unseen architect, the cosmic web. This layered, nested motion, our galaxy falling towards the Great Attractor, the center of Laniakea, which in turn is falling towards Shapley, reveals the true, underlying architecture of the universe. The cosmic web. On the largest scales, the universe isn't a uniform spray of galaxies. It resembles a gigantic, three-dimensional spider's web. This web consists of long, twisting filaments of dark matter and galaxies, stretching for hundreds of millions of light-years. Where these filaments connect, they form dense, brilliant hubs, the superclusters like Laniakea and Shapley. In between are the great cosmic voids, immense, nearly empty regions of space. This structure is the natural result of gravity acting over billions of years. Tiny density differences in the early universe were amplified by gravity. Denser regions pulled in more matter, growing into the filaments and superclusters we see today, while less dense regions emptied out, becoming the voids. Our journey through the cosmos is not a random flight. We are traveling along one of these cosmic filaments. Our motion is being channeled by the largest structure in the universe. The pull we feel from the Great Attractor and the Shapley Supercluster is simply the pull of the densest parts of our local filament and the massive junction it connects to. We are being guided by an invisible architect. This realization is profound. Our motion isn't a strange anomaly. It's a fundamental clue to the universe's underlying order. The pull we feel is the pulse of the universe itself. The final twist. A race we can't win. So, here we are, flowing at 1.4 million miles per hour along a gravitational river toward the Great Attractor, which is itself being pulled toward the Shapley Supercluster. This leads to a final, inescapable question. What happens when we get there? Are we destined for a colossal, galaxy-shattering collision? It seemed our ultimate fate was to merge with countless other galaxies in a cosmic pile-up. But the universe had one more plot twist in store. A twist that changes everything. In 1998, astronomers made a discovery that won the Nobel Prize and turned cosmology on its head. They found that the expansion of the universe is not slowing down. It's accelerating. Something is actively pushing the universe apart, and on the very largest scales, it's winning the war against gravity. This mysterious, repulsive force was given a fittingly enigmatic name: dark energy. We still have almost no idea what it is, but we know it's powerful, making up nearly 70% of the universe. This is the ultimate twist. Yes, the gravity of the Great Attractor and Shapley is pulling us in. But at the same time, the very fabric of space between us and them is expanding, and that expansion is speeding up. So, will we ever reach our destination? The current answer is a mind-bending no. We are on a cosmic treadmill. We're running towards a finish line that's moving away from us faster than we can run. Our local gravitational pull is not strong enough to overcome the global, repulsive push of dark energy over these vast distances. Our fate, it seems, is not one of arrival, but of eternal travel. We are being pulled towards a destination that we can see, but can never reach. Our galaxy is destined to forever chase a ghost, drawn by the gravity of structures that dark energy is simultaneously pushing ever further from our grasp. In the unimaginably distant future, the accelerating expansion will have pushed all other superclusters so far away that their light will no longer reach us, leaving our local group of galaxies as a lonely island in an endless, empty void. The fact that we are moving at over 1,000,000 miles per hour isn't a threat. It's a revelation. It's a signpost, pointing to the unseen architecture that underpins reality. We are being pulled because we are part of something, a structure so immense and interconnected it defies our comprehension. We are travelers on a gravitational current, heading towards a destination we can see but will never reach. Our journey has no end. And perhaps that's the most profound discovery of all. The universe isn't a static map, but a dynamic, evolving story that is still being written. And we are moving right along with it. How galaxies move faster than light without breaking physics. If you get the chance to look up at a truly dark night sky, far away from city lights, you can see thousands of stars. With a decent telescope, millions. But what you're seeing is just a tiny fraction of what's out there. Beyond the stars of our own Milky Way or other galaxies. Hundreds of billions of them. Each one is a sprawling island of stars, gas, and dust, separated by gulfs of darkness so immense it takes light millions, or even billions, of years to cross them. For most of history, we thought the universe was a static, unchanging stage. Even Albert Einstein, when he cooked up his revolutionary theory of general relativity in 1915, assumed the universe was stable. His own equations, however, told a different story. They suggested a dynamic cosmos, one that should either be expanding or contracting. Uncomfortable with this, Einstein added a cosmological constant to force his equations to match the static universe. He believed in a move he later called his greatest blunder. Why a blunder? Because just over a decade later, an American astronomer named Edwin Hubble made a discovery that would tear down that static picture forever. He found proof that our universe isn't standing still. It's expanding. And in doing so, he uncovered a paradox so profound it seems to shatter one of the most fundamental laws of physics. Astronomers have found galaxies moving away from us faster than the speed of light. But wait, Einstein told us nothing can travel faster than light. So, are the laws of physics broken? Is our understanding of the cosmos completely wrong? The answer is a spectacular no, and it lies in a cosmic loophole, a secret of the universe hidden in the very fabric of reality. Understanding this secret will completely reshape how you see space, time, and your own place in the cosmos. The Gathering Storm. Hubble's redshift revolution. Our story really kicks off in the 1920s. While the world was dancing to jazz, astronomers were locked in a huge debate. They peered through powerful new telescopes and saw these faint, fuzzy patches of light they called spiral nebulae. Were these small gas clouds inside our own Milky Way, or were they, as a few people guessed, entire island universes? Galaxies just like ours, but unimaginably far away? Edwin Hubble was determined to settle it. He pointed the massive Hooker telescope at the Andromeda Nebula, the biggest and brightest of these smudges. Night after night, he was looking for a specific type of star, a Cepheid variable. These stars are special. They pulse, getting brighter and dimmer with a rhythm that's directly tied to their true brightness. By comparing how bright a Cepheid should be with how bright it looks from Earth, you can calculate its distance with incredible accuracy. They're the universe's standard candles. When Hubble found these stars in Andromeda and did the math, the result was staggering. Andromeda wasn't a nearby cloud. It was a full-blown galaxy, almost a million light-years away far outside the Milky Way. In that moment, the known universe expanded 100-fold. Those fuzzy nebulae were revealed to be billions of other galaxies. But that was just the first bombshell. As Hubble and others studied the light from these distant galaxies, they noticed something was off. The light was the wrong color. It was shifted. You know how the siren on an ambulance sounds high-pitched as it comes toward you, and then the pitch drops as it speeds away? That's the Doppler effect. It happens because sound waves get compressed as the source approaches and stretched as it recedes. Well, light is a wave, and it does the exact same thing. Light from something moving toward us is compressed, shifting its color to the blue end of the spectrum, a blue shift. Light from something moving away gets stretched, shifting it toward the red end, a red shift. When astronomers analyzed the light from these new galaxies, they found that almost all of them were redshifted. They were moving away from us. And here's the second, even bigger discovery. Hubble carefully measured the distances and recession speeds of dozens of galaxies and found a clear pattern. The farther away a galaxy was, the faster it was moving away. A galaxy 1 million light-years away recedes at a certain speed. A galaxy 2 million light-years away recedes twice as fast. This wasn't random. It was an orderly, systematic expansion. Hubble had discovered a fundamental law of the cosmos, now known as the Hubble-Lemaitre law. It's a simple but powerful equation. Velocity equals h0 times distance. V equals h0d. This was earth-shattering. The universe wasn't a static stage, it was growing. Every galaxy was rushing away from every other one. This became the first great pillar of the Big Bang theory. If everything is flying apart now, it must have all been crushed together in the past. But Hubble's law also planted the seeds of a deep and troubling paradox that seemed to challenge the very core of modern physics. The ultimate speed limit, Einstein's sacred law. To understand the paradox, you first have to appreciate the law it seems to break. It's hidden within the most famous equation in science. E equals mc squared. Einstein's special theory of relativity, published in 1905, did more than link mass and energy. It set a universal speed limit. Einstein's theory rests on a simple but radical idea. The laws of physics are the same for everyone, no matter how they're moving, and the speed of light in a vacuum, c, is also the same for every single observer. That sounds innocent, but the consequences are bizarre. Imagine you're on a train moving at half the speed of light and you turn on a flashlight. From your perspective, the light beam shoots away at speed c. But what about someone standing on the platform watching you fly by? Common sense says they should see the light moving at the speed of the train plus the speed of light. But they don't. Inexplicably, they also see that beam moving at c. For that to be possible, something has to give. That something is space and time. To the person on the platform, Time on your train appears to tick slower, and the train itself looks shorter. This isn't an illusion, it's real. Time and space are flexible, warping and stretching to make sure the speed of light stays constant for everyone. From this comes another critical consequence. As you push on an object with mass, its inertia, its resistance to changing speed increases. The faster it goes, the harder it is to make it go faster. As an object approaches the speed of light, its inertia heads towards infinity. You'd need an infinite amount of energy to get it across that final finish line. So, nothing with mass can ever reach the speed of light. Only massless particles like photons can travel at c. This is one of the most rigorously tested principles in science, confirmed daily in particle accelerators. It's the ultimate speed limit. Nothing, no spaceship, no planet, no galaxy can travel through space faster than light. And now we're at the heart of the problem. Hubble's law, V equals h0d, says a galaxy's speed is proportional to its distance. If you look far enough away, the math says the speed must eventually top the speed of light. The currently accepted value for the Hubble constant is around 70 kilometers per second per megaparsec. A megaparsec is 3.26 million light-years. This means for every 3.26 million light-years you look farther out, a galaxy appears to be moving 70 kilometers per second faster. If you do the math, you find a critical point known as the Hubble distance. At about 14 billion light-years, the recession speed hits 300,000 kilometers per second, the speed of light. Any galaxy beyond that is receding from us faster than light. In fact, astronomers estimate that up to 97% of the galaxies in our observable universe are moving away at superluminal speeds. So, what gives? Do we have an unbreakable law of physics clashing with observational proof that seems to shatter it? Are countless galaxies across the cosmos breaking Einstein's most sacred rule? This is the paradox. The resolution isn't that the law is wrong, but that our intuition about motion is incomplete. The answer is the cosmic loophole. The revelation. A cosmic loophole in spacetime. The solution to this puzzle lies in a crucial distinction. Einstein's speed limit says nothing can move through space faster than light. But it says nothing about the expansion of space itself. The galaxies aren't firing up rocket engines and blasting through space. They're more like passive passengers being carried by a current. That current is the expansion of spacetime itself. Imagine you're an ant on the surface of an uninflated balloon. You draw another ant an inch away. Now, start inflating the balloon. As the rubber stretches, the distance between the ants grows. They aren't walking away from each other. The very ground beneath their feet is expanding and carrying them apart. This is what's happening in our universe. Galaxies are the ants, and the fabric of spacetime is the balloon. The Big Bang wasn't an explosion in space. It was the beginning of the expansion of space everywhere. Let's refine that analogy. You're an ant on the balloon again. An ant 1 inch away, and another 10 inches away. You inflate the balloon so that every inch of rubber doubles in length every second. After 1 second, the ant that was 1 inch away is now 2 inches away, it moved 1 inch. But the ant that was 10 inches away is now 20 inches away, it moved 10 inches in the same second. From your perspective, the farther ant seems to be moving away much faster. This is exactly what Hubble's law describes. The galaxies aren't doing anything special. The space between us and a nearby galaxy is expanding a little. But there is vastly more space between us and a very distant galaxy. All that extra space is also stretching, and the effect is cumulative. It's like a chain of 1,000,000 tiny rubber bands all stretching at once. The total speed adds up over the entire length. This is the loophole. A distant galaxy isn't breaking the speed limit because it isn't traveling in the normal sense. Its motion relative to its immediate neighbors is still well below light speed. It's just embedded in a patch of spacetime that, from our perspective, is being carried away by the expansion of all the space in between. No information is moving through space faster than light. Special relativity is safe. Another great analogy is raisin bread dough baking. As the dough rises, every raisin moves away from every other raisin. A raisin on one side of the loaf would see a nearby raisin move away slowly, while one on the far side would recede much more quickly. And crucially, there's no center to this expansion. Every raisin sees all other raisins moving away from it. This illustrates the cosmological principle. On the largest scales, the universe looks about the same everywhere and in every direction. The expansion is happening everywhere. So when we see galaxies receding faster than light, we're not seeing physics break. We're seeing a direct consequence of Einstein's own theory of general relativity. We are witnessing the fabric of reality itself stretch. The observable horizon in a future sky. This stretching of space-time has huge consequences for what we can, and can't, ever see. As light travels from distant galaxies through this expanding space, it gets stretched. This is the cosmological redshift. A photon that leaves a galaxy as high-energy blue light might travel for billions of years, and by the time it reaches us, it's been stretched into a low-energy red or even infrared photon. Now, think about a galaxy so far away it's receding faster than the speed of light. What happens to the light it emits? A photon leaves that galaxy, traveling toward us at light speed. But the space it's traveling through is expanding away from us faster than light speed. It's like trying to run up a downward escalator that's moving faster than you can run. You're making progress on the steps, but relative to the ground floor, you're still moving backward. This creates a cosmic boundary. There's a region of space called the observable universe, a sphere containing all the galaxies whose light has had enough time to reach us in the 8 billion years since the Big Bang. But because space has been expanding that whole time, the galaxies that emitted the most distant light we see are now estimated to be about 46 billion light-years away. Beyond this horizon, there are almost certainly more galaxies, but we will never see them. But the situation is getting even stranger. In the late 1990s, astronomers were observing distant Type Ia supernovae exploding stars that are fantastic standard candles. They expected to find that the universe's expansion was slowing down due to gravity. They found the exact opposite. The distant supernovae were even fainter, and therefore farther, than predicted. This meant only one thing. The expansion of the universe is speeding up. This shocking discovery, which earned its leaders the 2011 Nobel Prize in Physics, introduced a new mystery: dark energy. Something must be pushing spacetime apart, overpowering gravity on the largest scales. We still don't know what it is, but we can measure its effects. It seems to be a property of space itself, making up about 68% of the universe's total energy density. The rest is about 27% dark matter, another mystery, and a mere 5% is the ordinary matter that makes up you, me, and the stars. This acceleration means there's a cosmic event horizon that's effectively closing in. Galaxies that are currently visible but very far away will one day cross this boundary. The space between us will expand so fast that their light will no longer be able to reach us. They will vanish from our sky forever. Imagine the sky in the far future. An astronomer might look out and see only our own local group of galaxies. Everything else will have been pushed beyond the horizon, its light redshifted into nothingness. They might conclude they live in a small, static, island universe, with the evidence of our vast, dynamic cosmos erased forever. Local motion versus the grand cosmic flow. So you might be asking a perfectly reasonable question. If everything is expanding, why isn't the Earth moving away from the Sun? And what about Andromeda? I thought it was on a collision course with us. This is where we have to separate the large-scale, Hubble flow, from local motion. The expansion of spacetime is a relatively gentle force, but it's relentless over vast distances. On smaller scales, other forces easily overpower it. The forces holding atoms and planets together are vastly stronger than cosmic expansion. Your body isn't expanding, and neither is the Earth. Gravity also dominates locally. The planets are gravitationally bound to the Sun. The Sun is one of hundreds of billions of stars bound together in the Milky Way. And the Milky Way is part of the local group, a cluster of over 50 galaxies all held together by their mutual gravity. Within this local group, the cosmic expansion is completely overwhelmed. Andromeda is indeed moving towards us at about 300 kilometers per second, and our two galaxies are set to merge in about 4.5 billion years. This is its peculiar velocity, its own local movement, separate from the Hubble flow. It's only when you zoom way out, far beyond our local neighborhood, that you see the Hubble flow take over. On scales of billions of light years, the individual gravity of galaxies becomes negligible compared to the cumulative stretching of spacetime. There, gravity may pull galaxies into massive clusters and filaments, forming a cosmic web, but the web itself is being stretched apart. The ongoing mystery, the Hubble tension. Science is never really settled, and the story of our expanding universe is a perfect example. In recent years, a new puzzle has emerged: the Hubble tension. The problem is that our two best methods for measuring the Hubble constant, h0, give slightly different answers. One method looks at the early universe. By studying the cosmic microwave background, CMB, the afterglow of the Big Bang, scientists can use our standard model of cosmology to predict what the expansion rate should be today. This method consistently gives a value around 67 or 68 kilometers per second per megaparsec. The other method looks at the late universe. This is the direct approach pioneered by Hubble, using standard candles like Cepheid variables and supernovae to measure the distances and speeds of nearby galaxies. This method, refined by the Hubble and James Webb Space Telescopes, consistently gives a higher value, around 73 or 74 kilometers per second, MPC. The discrepancy is small, but it's statistically significant and refuses to go away. The James Webb Telescope has largely confirmed the late universe measurements, ruling out simple error. This is a genuine crisis in cosmology. It might mean our standard model is missing something. Maybe dark energy isn't constant, or maybe there's a new particle or force we haven't discovered yet. Scientists are attacking this problem from all angles. The Euclid mission is mapping billions of galaxies to trace the history of cosmic expansion. Others are using gravitational waves from merging black holes called standard sirens to get a totally independent measurement. The Hubble tension is a perfect example of science in action. It's a clue, and pulling on that thread could lead to a whole new understanding of the universe. The universe is just filled with these incredible, mind-stretching mysteries. From galaxies moving faster than light to the enigma of dark energy and the Hubble tension, we are constantly being shown that reality is far stranger and more wonderful than we ever could have imagined. If you want to keep exploring the frontiers of science with us, be sure to subscribe and hit that notification bell so you don't miss our next journey into the unknown. And let us know in the comments, what's the most mind-bending fact about the universe you've ever heard? So, how do galaxies move faster than light without breaking physics? The answer is both simple and incredibly deep. They don't, at least, not in the way we think. The ultimate speed limit, c, governs motion through space, and that law is absolute. The cosmic loophole is that space itself is not fixed. It's a dynamic, stretching fabric, and on the largest scales, it's accelerating. The galaxies we see hurtling away from us at impossible speeds are just passengers on this expanding cosmic river. They aren't violating any laws. They're revealing the true nature of the universe, one that began in a hot, dense state 13 8 billion years ago and has been expanding and cooling ever since. From Hubble's revolutionary discovery to the modern puzzle of the Hubble tension, the story of our universe is a story of human curiosity pushing against the boundaries of knowledge. We live in a cosmos where 95% of its contents, dark matter and dark energy, remain a profound mystery. A cosmos where most galaxies are already receding from us faster than light, carried away on the swelling tide of spacetime, their light forever beyond our reach. The next time you look up at the stars, remember you aren't standing still. You're riding on a planet, orbiting a star, in a galaxy that's part of a local cluster, all while the very fabric of reality itself stretches out beneath you. It's a humbling and awe-inspiring thought. We are all in motion, together, in an expanding universe. The universe has a speed limit of 0. Take a look at something in the room with you that's perfectly still. Or is it? What if I told you that in our universe, true stillness is impossible? That everything in existence, even at the coldest temperature imaginable, absolute 0, is doomed to wiggle and jiggle for all eternity. Now, this isn't some philosophical riddle. It's a fundamental rule of reality, woven into the very fabric of space and time. The story of why the universe has a speed limit of 0, why it's forbidden from ever holding perfectly still, is one of the strangest and most fascinating tales in all of science. It's the story of a mysterious energy that keeps the cosmos alive with motion, even in its coldest, darkest corners. This is the story of zero-point energy, the classical world of motion. To get why nothing can ever truly stop, we first have to understand why anything moves in the first place. And for that, we can forget the quantum realm for a minute and start with something much more familiar: a simple cup of coffee. When you touch a hot mug, that feeling of heat isn't some abstract thing. It's a microscopic storm. The atoms making up that ceramic mug aren't just sitting there politely. They are vibrating, shaking, and slamming into their neighbors trillions of times a second. When your fingers touch the mug, that frantic motion gets transferred to the atoms in your skin. Your nerves register this chaotic bombardment of energy as heat. The faster the wiggle, the hotter it feels. This idea is the bedrock of thermodynamics. Temperature is motion. More specifically, it's a measure of the average kinetic energy, the energy of movement of all the particles in a substance. Think about the states of matter. In a gas, like the steam rising from your coffee, the molecules are like hyperactive toddlers in a bouncy castle. They're zipping around freely, constantly bouncing off each other. The air molecules in the room around you right now are moving, on average, at over 1,000 miles per hour faster than the speed of sound. Cool things down, and you get a liquid, like the coffee itself. Here, the molecules are closer together, like a crowded dance floor. They can't fly free anymore, but they slide and slither past one another, still full of energy. Finally, in a solid, like your spoon, the atoms are locked into a rigid grid, a crystal lattice. They can't roam around at all. But that doesn't mean they're still. They're like kids strapped into their car seats. They can't run around the car, but they can, and absolutely will, wiggle and vibrate in their fixed positions. When you heat up that spoon, you're just making those atoms vibrate more violently. This is actually why most things expand when they get hot. The atoms are shaking so much they push their neighbors farther away. So, whether it's a gas, a liquid, or a solid, everything is a frenzy of unseen motion. Heat flows from hot to cold simply because the faster-moving particles of the hot thing crash into the slower-moving particles of the cold thing, giving them a little kick of energy until they all even out. It's all just a cosmic game of bumper cars. This classical picture leads to a very logical question. If temperature is motion, what happens if we just keep removing the heat? If we slow those atoms down, and then slow them down some more? Eventually, we should reach a point where all the motion stops. A point of perfect, absolute stillness. This theoretical point is called absolute zero. The quest for absolute zero. The idea of an ultimate cold started taking shape back in the 18th and 19th centuries. Scientists studying gases noticed that when you cool a gas, it shrinks. They did the math and realized that if you kept going, you'd eventually hit a temperature where the gas volume would theoretically shrink to zero. That didn't make sense, but it did suggest there was a floor, a lowest possible temperature. That temperature was calculated to be about minus 273, 15 degrees Celsius, or minus 459, 67 Fahrenheit. This wasn't just a number, it became a holy grail for physicists. The race to absolute zero was one of the great scientific adventures of the early 20th century. And the challenge was immense. You can't just put something in a colder freezer, because how do you make the freezer itself colder? Every step closer required inventing entirely new ways to get cold. Pioneers like James Dewar and Heike Kamerlingh honest developed techniques to turn permanent gases into liquids. They conquered oxygen, then nitrogen, then hydrogen. Finally, in 1908, Kamerlingh honest did it. He liquefied helium at a mind-bogglingly cold 4.2 degrees above absolute zero, or 4.2 Kelvin. And down at these temperatures, the world gets weird. As materials got colder, they started showing bizarre new properties. In 1911, Onnes himself discovered that the electrical resistance of mercury completely vanished below 4.2 Kelvin. He called it superconductivity. It was a peek into a world where the normal rules of physics seemed to bend. And the race continued. Physicists developed even crazier techniques. Dilution refrigerators, laser cooling, you name it. Each new method shaved off another tiny fraction of a degree. Today, labs have reached temperatures in the nanokelvin and even picokelvin range that's just billionths or trillionths of a degree above absolute zero. In this frozen realm, matter acts in ways that defy all common sense. Atoms, slowed to a crawl, can merge into a single quantum state called a Bose-Einstein condensate, where millions of individual atoms start behaving like one giant superatom. Liquids become superfluid, flowing without any friction and climbing right up the walls of their containers. It seemed like physicists were just about to cross the finish line. They were ready to finally achieve that state of perfect rest, where all atomic motion would stop, and the universe would, just for a moment, hold perfectly still. But as they got closer and closer to that final point of zero, they slammed headfirst into a wall. A wall made not of matter, but of a fundamental law of nature. It turned out the dream of perfect stillness was, and always would be, impossible. The universe, it seems, had other plans. The quantum wall. According to classical physics, at 0 Kelvin, everything should be simple. The atoms in a crystal should come to a complete and utter stop. Zero kinetic energy. Zero momentum. Perfectly, unambiguously still. But that's not what happens. As scientists got better and better at cooling things, they noticed something stubborn. No matter how close they got to absolute zero, their systems refused to settle down completely. There was always a little residual jiggle, a faint, unquenchable tremor that no amount of cooling could get rid of. This wasn't an equipment failure. It wasn't some leftover heat they couldn't find. It was a sign that they had crossed a boundary, leaving the familiar world of classical physics and stumbling into the bizarre landscape of the quantum world. The problem wasn't in the lab. The problem was in the laws of physics. The classical idea of perfect stillness was just plain wrong. And the reason why goes right to the heart of what it means for anything to exist at all. To understand why the universe is forbidden from holding still, we have to meet one of the most famous, and most misunderstood, principles in all of science. The Heisenberg uncertainty principle. In 1927, a German physicist named Werner Heisenberg completely changed our view of reality. He introduced the uncertainty principle, and in its most famous form, it says something both simple and profound. It is impossible to know both the precise position and the precise momentum of a particle at the same time. Let's unpack that. Momentum is just mass times velocity, so this is really about a particle's location and its motion. The principle doesn't say our measurement tools are too clumsy. It says that nature itself has a fundamental, built-in, fuzziness. The more you pin down a particle's location, the less you can possibly know about its motion, and vice versa. Think of it like trying to measure a single note in a piece of music. If you want to know the exact pitch, or frequency, you have to listen to the sound wave for a little while. A single, instantaneous snapshot of the wave doesn't tell you its frequency. The more accurately you want to know the pitch, the longer the sample you need. But taking a longer sample means you're less certain about the exact moment in time that note occurred. There's a trade-off. In quantum mechanics, position and momentum have a similar relationship. So what on earth does this have to do with absolute zero? Everything. Let's imagine for a second that a particle could be perfectly still. That would mean its velocity is exactly zero. And if its velocity is zero, its momentum is also exactly zero. There would be zero uncertainty in its momentum. Well, according to Heisenberg's principle, if the uncertainty in momentum is zero, the uncertainty in its position must be infinite. A particle that is perfectly still would have to be located everywhere in the universe at once. Which makes no sense. Let's flip it around. Imagine we try to force a particle to be still by trapping it. Let's take an atom in that crystal lattice. We know its position pretty precisely. It's stuck in that little spot in the grid. So its uncertainty in position is very small. Because of the uncertainty principle, pinning down its position forces a huge increase in the uncertainty of its momentum. Its momentum is no longer allowed to be precisely zero. It now has a whole range of possible momentums, and that range gets bigger the more we confine the particle. And since momentum is tied to energy, this means the particle must have some kinetic energy. Zero is not an option. The very act of confining a particle to a place guarantees that it has to be moving. This isn't just a quirky rule, it's what keeps you from falling through the floor. Classically, the electrons in an atom should radiate away their energy and spiral into the nucleus in less than a second, causing all matter to collapse. The uncertainty principle prevents this. If an electron fell into the nucleus, we'd know its position with incredible precision. This would force its momentum and therefore its energy to become enormous, more than enough to shoot it right back out. So the electron settles for a compromise, an orbit, or more accurately, a probability cloud, where its energy is at the lowest possible level that doesn't violate the uncertainty principle. And this brings us right to the heart of the mystery. This lowest possible energy, the energy that a quantum system can never, ever lose, has a name. It's called zero-point energy. Zero-point energy. The universe's hum. Zero-point energy, or ZPE, is the lowest possible energy a quantum system can have. It's the energy of its ground state. And thanks to Werner Heisenberg, that ground state energy is never zero. Think of a guitar string. It can only vibrate at specific frequencies, a fundamental note and its harmonics. It's quantized. You can't make it vibrate at a frequency between those notes. A quantum system is similar, it has distinct, quantized energy levels. But unlike the guitar string, which can be perfectly still with zero energy, the quantum system's lowest possible energy level is always greater than zero. This is the source of that unquenchable jiggle. Even at absolute zero, when you've sucked out all the thermal motion, the atoms in a solid are still trapped in their crystal lattice. That confinement, as we just saw, means their momentum can't be zero. They must continue to vibrate with their zero-point energy. It's a fundamental, inescapable quantum jitter. And this doesn't just apply to particles. It applies to everything in quantum physics, including the fields that fill the universe. According to quantum field theory, the universe is made of continuous, fluctuating fields. There's an electron field, a photon field, the electromagnetic field, and so on. What we think of as a particle is just a localized, excited vibration in its field. So what happens when there are no particles? What about the vacuum of empty space? Classically, a vacuum is just nothing. Empty. But in quantum field theory, the vacuum isn't empty at all. It's simply the ground state of all those quantum fields. And just like our atom in a crystal, the ground state energy of these fields is not zero. The vacuum itself hums with zero-point energy. At every single point in space, there is a sea of these zero-point fluctuations, often called the quantum foam. You can imagine the vacuum as a seething, bubbling cauldron of virtual particles. These aren't real particles you can catch. They are fleeting fluctuations of energy pairs of particles and antiparticles that borrow energy from the vacuum to pop into existence, exist for an unimaginably short time, and then annihilate each other, paying back their energy debt. Empty space is not empty. It's a frantic, constant dance of virtual particles flickering in and out of reality. The universe, even in its most desolate voids, is never, ever quiet. This sounds like science fiction, a mathematical fantasy. But it's not. The existence of zero-point energy has real, measurable consequences. We know it's there because we can see what it does. Evidence and effects of zero-point energy. For a while, many physicists just ignored zero-point energy, treating it like a mathematical quirk. But several key discoveries proved it's very real. The most famous piece of evidence is the Casimir effect. In 1948, the Dutch physicist Hendrik Casimir was trying to figure out why certain microscopic particles in a liquid were clumping together. His calculations weren't working. He mentioned it to the legendary Niels Bohr, who mumbled something about zero-point energy. A light bulb went off for Casimir. He made an incredible prediction. Imagine you take two perfectly smooth, uncharged metal plates in a perfect vacuum and place them incredibly close together. Classically, nothing should happen. But Casimir realized the quantum foam changes things. Outside the plates, virtual particles of all kinds can pop in and out of existence. But the tiny gap between the plates acts like a filter. Only virtual particles with wavelengths that fit neatly into the gap are allowed. All others are excluded. This means there are more virtual particles popping into existence outside the plates than between them. This imbalance creates a pressure. The vacuum outside pushes the plates together more than the vacuum inside pushes them apart. The result is a tiny, but measurable, attractive force, created purely by the energy of empty space. This bizarre prediction was eventually verified with incredible precision. The Casimir effect is direct proof that the vacuum is not empty. Another stunning piece of evidence is helium. Every other substance in the universe, if you cool it down enough, will eventually freeze solid. But not helium. At normal atmospheric pressure, even if you could cool it all the way to absolute zero, helium would remain a liquid. Why? Zero-point energy. Helium atoms are very light and the forces holding them together are incredibly weak. Even at absolute zero, their fundamental quantum jiggle, their zero-point energy is so great that it overcomes those weak attractions. The atoms simply vibrate too much to ever lock into a solid crystal. You can force helium to solidify, but you have to apply about 25 times normal atmospheric pressure just to squeeze the atoms together hard enough to overcome their zero-point motion. Zero-point energy isn't a ghost. Its fingerprints are all over the quantum world, from the forces between metal plates to the subtle energy shifts in a hydrogen atom, and it's the only reason helium stays liquid forever. The cosmic implications. The consequences of this cosmic restlessness go way beyond the lab. The fact that the universe has a speed limit of zero, that nothing can be truly still, has profound implications for the entire cosmos. For one, the very stability of the atoms that make you, me, and everything we see is a direct result of zero-point energy. That quantum jitter is what prevents electrons from collapsing into the nucleus, ensuring that matter can exist at all. Without it, the universe would have been a featureless soup. But the biggest, most baffling implication of zero-point energy comes from cosmology. We've established that the vacuum of space should be filled with a colossal amount of this energy. And according to Einstein's theory of general relativity, all energy has gravity. So, this enormous energy in the vacuum should be warping spacetime on a massive scale. It should be causing the universe to expand or collapse at a truly catastrophic rate. When physicists first tried to calculate how much energy the vacuum should have, they got a number that was just wrong. It was so wrong it's hard to even talk about. It was about 120 orders of magnitude. That's a 1 with 120 zeros after it, larger than what we actually observe. This gap between theory and reality is known as the cosmological constant problem, or the vacuum catastrophe. It has been called the worst theoretical prediction in the history of physics. Something is clearly missing from our understanding. Maybe some unknown physics is canceling almost all of it out. What's so tantalizing is that in 1998, astronomers discovered that the expansion of the universe is actually accelerating. This implies there is a tiny bit of energy in the vacuum, what we now call dark energy, that's pushing everything apart. So the vacuum does have energy, and it does have a gravitational effect. It's just trillions upon trillions of times weaker than our theories predict. Solving this mystery is one of the biggest goals in all of science. It's a giant sign pointing to a deep connection between the world of the very small and the cosmos of the very large that we just don't get yet. And at the center of it all is zero-point energy, the fundamental, unquenchable hum of the universe. It's pretty mind-bending, right? We've gone from the jiggling atoms in a coffee cup to the quantum foam of empty space, all to understand one simple truth. Nothing is ever truly still. And this restlessness isn't a flaw, it's the feature that makes existence possible. If this journey into the quantum weirdness sparked your curiosity, make sure you subscribe and ring that notification bell, because we explore the biggest ideas in the universe every week. Now I want to hear from you. What part of zero-point energy just completely breaks your brain? The plates moving in a vacuum? The fact that helium won't freeze? Or the 120 zero problem? Let me know in the comments. So, the next time you see something that looks perfectly motionless, remember the truth. If you could zoom in far enough, past the limits of sight, you'd find a world in constant, frantic motion. A world where atoms vibrate in their cages, and even the empty space between them is a seething ocean of virtual particles flickering in and out of being. We started with a simple idea. Heat is motion, so no heat should mean no motion. But we found that at the very bottom of reality, there's a hard limit. A quantum rule, dictated by the uncertainty principle, that forbids perfect rest. This rule creates zero-point energy, the irreducible, fundamental energy that the universe can never get rid of. This energy stops atoms from collapsing, keeps helium a liquid at absolute zero, pulls metal plates together out of nothing, and even plays a role in the expansion of our cosmos. The universe has a speed limit, but it's not at the top end. It's at the bottom. The ultimate speed limit is zero, and it's a limit that can never be reached. The universe is fundamentally, and beautifully, restless. It is always humming, always vibrating, always alive with the silent, invisible music of the quantum world. The absolute zero paradox. We all think we know what off means. You flip a switch, the light goes out. You press a button, the television screen goes dark. You turn down the thermostat, the air conditioner's relentless hum ceases, and the room gets cold. For over a century, scientists were convinced they had found the universe's ultimate off switch. A final, fundamental stop sign for reality itself. It's a temperature, a concept, an absolute limit called absolute zero. The coldest anything can possibly get, where all the jiggling, all the buzzing, all the frantic motion that makes up reality just stops. For decades, scientists chased this ghost. A temperature of -273, 15 degrees Celsius, the theoretical point where all motion in the universe was supposed to stop. They thought they had found reality's off switch. But when they zoomed all the way in, when they built machines that could peer into the deepest, coldest states of existence, they discovered something astonishing. The universe can't be turned off. In fact, what happens at the coldest temperatures imaginable shatters our understanding of what's real. So, what did they find at the very edge of existence? The answer isn't just some simple twist in a physics textbook. It's a paradox that strikes at the heart of reality, revealing that the universe has a secret, a persistent, unquenchable hum that can never, ever be silenced. The classical dream of stillness. To understand why this is such a mind-blowing revelation, we have to travel back in time. Back to a world lit by gas lamps and powered by steam, where the very nature of heat and cold was one of science's greatest mysteries. The 19th century was an era of titanic machines and bold new theories. Physicists were grappling with the forces driving their new industrial age, codifying the laws of thermodynamics, the science of heat, work, and energy. At the center of it all was a simple, intuitive idea: heat is motion. When something is hot, its atoms and molecules are jiggling and vibrating chaotically. The steam powering a locomotive was just water molecules, agitated into a frenzy. The warmth from a fireplace was the energetic dance of air particles. It follows, then, that cold must be the opposite. Cold is stillness. As you remove heat from something, its particles slow down. The frantic dance becomes a gentle sway, then a slow wobble, and finally, if you could just keep going, a complete and utter stop. This line of thinking led to a powerful and logical conclusion. There must be a floor to temperature. A point of ultimate cold where all this atomic motion ceases entirely. You couldn't get any colder, because there'd be no more motion to remove. This theoretical endpoint was first seriously proposed and calculated in the mid-1800s by the brilliant British physicist William Thomson, later known as Lord Kelvin. Kelvin, building on the work of others who had noticed how gases contract as they cool, extrapolated this behavior. He realized that if you kept cooling a gas, its pressure would decrease in a predictable line. Plot that on a graph, and the line marches steadily downwards until it hits one inevitable point: zero pressure. At that point, the gas particles would, in theory, have no energy left to push against their container. They would have stopped moving. Kelvin calculated this point to be approximately -273 degrees Celsius. He called it absolute zero, and proposed a new temperature scale starting from this fundamental point, a scale we now call the Kelvin scale in his honor. Today, absolute zero is, by definition, exactly -273, 15 degrees Celsius, or simply 0 K. This idea was more than a mathematical curiosity, it was a grand, romantic quest. It represented a state of perfect tranquility, a finality that deeply appealed to the orderly Victorian mind. To reach absolute zero was to conquer the last frontier of cold, to find the universe's off switch. The race was on. Scientists across Europe began a frantic competition to liquefy gases, each step bringing them closer to this ultimate goal. They developed ingenious cascades of cooling systems, using the evaporation of one liquid to cool and condense a more stubborn gas, which was then used to tackle the next. James Dewar liquefied hydrogen in 1898, reaching a frigid 20 Kelvin. But the final prize, helium, the most resistant gas of all, held out until 1908, when the Dutch physicist Heike Kamerlingh Onnes finally tamed it, bringing the world down to just 4 Kelvin. With each milestone, the world at low temperatures revealed itself to be an increasingly strange place. Onnes himself discovered that at these temperatures, some materials suddenly lose all resistance to electricity, a phenomenon he dubbed superconductivity. It was as if the normal rules of the world were being suspended. These were the first hints that the journey toward absolute zero wasn't just about reaching a state of stillness, but about entering a whole new realm of physics. The classical dream was beautiful in its simplicity. Cool something down, its atoms slow down. Reach absolute zero, they stop. The end. A perfect, frozen, silent universe. For decades, this was the undisputed picture of reality at its coldest. The quest continued, with physicists building ever more sophisticated refrigerators, laser cooling systems, and magnetic traps, inching ever closer to that final, elusive degree. They were chasing the ghost of perfect stillness. But as they crept to within billionths of a degree of absolute zero, they didn't find the silent, motionless world that Kelvin had envisioned. They found something else entirely. Something buzzing with an energy that refused to die. Something that proved the classical dream was not just wrong, but fundamentally impossible. The universe, it turned out, had a very different idea about what off really means. The first cracks in reality. The first tremors that would shatter the classical dream of absolute zero began not in cryogenics labs, but in the minds of theoretical physicists at the turn of the 20th century. Physics was in turmoil. A series of baffling experimental results from the nature of light from hot objects to the behavior of electrons simply refused to fit the established rules. The universe, when you looked at it very closely, seemed less like a predictable clockwork machine and more like something weird. This was the dawn of the quantum revolution. It began with Max Planck, who proposed that energy wasn't continuous, but came in discrete packets, or quanta. Then came Albert Einstein, who took this idea and ran with it, showing that light itself could be thought of as a particle, a photon. Suddenly, the solid ground of classical physics began to feel like quicksand. The old rules were breaking down, and a new, bizarre set of rules was emerging. At the very heart of this new quantum weirdness was a principle that would be the ultimate destroyer of classical stillness. It's called the Heisenberg uncertainty principle, and it's one of the most profound and mind-bending discoveries in the history of science. In 1927, the German physicist Werner Heisenberg formulated this principle, delivering a fatal blow to our classical intuition. In simple terms, the uncertainty principle states that there's a fundamental limit to how much you can know about a particle's properties at the same time. Specifically, you cannot know both a particle's exact position and its exact momentum, its mass times its velocity, simultaneously. This isn't a limitation of our tools. It's not that our rulers are too clunky or our speed guns too slow. Heisenberg's principle says this uncertainty is an inherent, baked-in feature of reality itself. The more precisely you pin down a particle's location, the less precisely you can know its momentum, and vice versa. It's a cosmic trade-off. Nature enforces a fundamental fuzziness at the quantum level. Imagine trying to see an electron. You have to bounce something off it, like a photon. But an electron is so tiny that even a single photon hitting it is like a bowling ball hitting a ping-pong ball. The very act of measuring its position gives it a massive kick, sending it flying off in some unknown direction with an unknown momentum. So, the moment you know where it was, you've completely lost track of where it's going. Okay, so you try to be gentler. You use a low-energy photon with a long wavelength. This won't disturb the electron's momentum as much. But there's a catch. The long wavelength of that photon means you can no longer pinpoint the electron's position with any accuracy. It's like trying to find a single grain of sand on a beach using a giant, blurry beach blanket. You know the grain is under there somewhere, but its exact position is now highly uncertain. This is the eternal quantum balancing act. Precision in position costs you certainty in momentum. Certainty in momentum costs you precision in position. You can't have both. The universe simply forbids it. For a long time, this seemed like a philosophical curiosity, a strange rule for the subatomic world that didn't have much bearing on our big, clunky reality. Of course, you can know the position and speed of a baseball. That's because for large objects, the uncertainty is so infinitesimally small it's completely unnoticeable. The fuzziness is there, but it's a million times smaller than the object itself. But what happens when we connect this bizarre quantum rule back to our quest for absolute zero? What does the uncertainty principle have to say about a state of perfect stillness? This is where the classical pursuit of cold and the new quantum reality collide head-on. Let's reconsider that classical dream. At absolute zero, all motion ceases. Every particle comes to a perfect, complete stop. Its kinetic energy is zero, which means its momentum is also precisely zero. It's not moving. And if it's not moving, it must be sitting perfectly still in a single location. So, at the classical absolute zero, we would know a particle's momentum with perfect certainty, its zero, and its position with perfect certainty. See the problem? A particle at classical absolute zero would have a perfectly defined position and a perfectly defined momentum. This is a direct, blatant, and catastrophic violation of the Heisenberg uncertainty principle. According to the fundamental laws of quantum mechanics, it's impossible. This wasn't just a minor wrinkle, it was a cosmic contradiction. The quest to find the universe's off switch had led scientists to a state that the universe itself said couldn't exist. The very laws of physics that govern reality were screaming that perfect stillness is forbidden. This meant one of two things had to be wrong. Either the Heisenberg uncertainty principle, a cornerstone of the most successful scientific theory in history, was incorrect, or our century-old understanding of absolute zero was completely flawed. As experiments pushed ever closer to that impossible temperature, the evidence mounted, and the conclusion became inescapable. It wasn't quantum mechanics that was wrong. It was our dream of a silent, motionless universe. The revelation at the bottom. So, if perfect stillness is forbidden, what actually happens down there, at the coldest possible temperature? If the universe refuses to turn off, what state does it settle into? The answer is a shocking truth called *0-point energy. Because the uncertainty principle forbids a particle from having both a definite position and zero momentum, it can never truly stop. It's forced into a state of perpetual, irreducible motion. Even at absolute zero, when all thermal energy, all the energy we think of as heat, has been stripped away, a minimum amount of vibrational energy remains that simply cannot be removed. This is the 0-point energy. It is the cost of existing in a quantum universe. Think of a tiny ball on a spring. Classically, if you cool the system, the ball will settle perfectly still at the bottom, motionless. Its energy would be zero. But in the quantum world, this is impossible. To be perfectly still at the bottom means its position and momentum are both known. The uncertainty principle recoils at this. So the particle compromises. It spreads out into a quantum fuzz, a haze of probability around the lowest point. It's never in one precise spot but exists as a blur of potential locations. To maintain this blur, it must constantly jiggle. This residual, inescapable jiggling is the 0-point energy. It's not heat. It's a fundamental, ghostly hum baked into the fabric of reality. Liquid helium is a stunning real-world example. Its 0-point energy is so significant that it prevents the helium from freezing into a solid at normal pressure, no matter how cold you make it. It remains a liquid all the way down to absolute zero, a quantum liquid jiggling with energy it can never lose. This isn't just a theoretical abstraction. 0-point energy is real, with observable consequences. The most compelling proof is the *Casimir effect. Predicted by Dutch physicist Hendrik Casimir in 1948, the effect is as strange as it is undeniable. Imagine, empty, space, a perfect vacuum. According to quantum field theory, this vacuum isn't empty at all. It's a seething cauldron of virtual particles and fluctuating energy fields. Particles are constantly popping into existence, existing for a fleeting moment, and then annihilating each other. This roiling sea of potential is the physical manifestation of the vacuum's zero-point energy. Casimir asked, "What happens if you place two uncharged, parallel metal plates very close to each other in this vacuum? Outside the plates, virtual photons of all wavelengths can exist. But between the plates, only virtual photons whose wavelengths fit a whole number of times into the gap are allowed. All other wavelengths are excluded. This means there are fewer quantum fluctuations between the plates than outside them. The result is a net force, an attraction, pushing the two plates together, a purely quantum force generated from the energy of nothing. And it has been measured. In 1997, a delicate experiment confirmed the Casimir force to within 5% of its predicted value. Two plates, moved together by the energy of empty space. As physicists got even closer to absolute zero, they discovered entirely new states of matter. The most famous is the Bose-Einstein condensate or Beck. First theorized by Satyendra Nath Bose and Albert Einstein in the 1920s, they predicted that if you cool a gas of certain particles, bosons, to just a sliver above absolute zero, something extraordinary would happen. As the particles get colder, their quantum waves start to spread out and overlap. At a critical point, just billionths of a degree above 0 Kelvin, the atoms lose their individual identities and condense into a single, massive, superatom. For 70 years, this was just a dream. But in 1995, Eric Cornell and Carl Wieman created one with rubidium atoms, cooled to a staggering 170 nanokelvin. Thousands of individual atoms suddenly coalesced into one coherent matter wave. Its quantum mechanics made visible. But the weirdness doesn't stop there. The chase for absolute zero revealed even more paradoxical states, like the supersolid. This is a material that is simultaneously a rigid, ordered solid and a superfluid that can flow without any friction. How could something be both at once? After early hints proved complex, research groups starting around 2017 successfully created and observed this state in ultracold atomic gases. They coerce atoms into a series of dense, crystal-like droplets that maintain a rigid pattern, the solid part. But at the same time, atoms can flow without friction between these droplets, the superfluid part. More recently, scientists have even pushed the boundaries by creating a version of this bizarre dual state by coupling light with matter, forcing photons into a supersolid-like phase. So, the universe doesn't have an off switch. As we approach the bottom of temperature, reality doesn't stop, it transforms. It's a world where nothing is ever truly still, where empty space can push on metal plates, and where matter can be a solid that flows like a liquid. The paradox of absolute zero is that the point of minimum energy isn't a point of maximum silence, but a gateway to the loudest, most bizarre concert in the cosmos. The universe's hum and our reality. The implications of this unquenchable zero-point hum ripple out from ultracold labs and touch nearly every aspect of the cosmos. This isn't just a quirky exception, it's one of the most fundamental rules there is. Let's start with the vacuum of space. We've established it's not empty, but a froth of zero-point energy. This, vacuum energy, is a prime suspect for one of the biggest puzzles in modern physics. Dark energy. Observations show the expansion of the universe is accelerating, pushed apart by some mysterious anti-gravitational force. One leading candidate for dark energy is the zero-point energy of the vacuum itself. The problem is, when physicists try to calculate how much zero-point energy should be in the vacuum, they get a number that is spectacularly, outrageously wrong. Their answer is bigger than the observed value by a 1 with about 120 zeros after it. This discrepancy, known as the cosmological constant problem, is called the worst theoretical prediction in the history of physics, and tells us we're missing something profound about how quantum mechanics and gravity connect. The zero-point hum also underpins the stability of matter itself. In a classical world, the electron in a hydrogen atom should radiate its energy away and spiral into the proton in a fraction of a second. Atoms shouldn't be stable. Quantum mechanics, and specifically zero-point energy, provides the solution. The electron exists as a wave of probability. Thanks to the uncertainty principle, it can't fall into the proton, as that would mean its position and momentum would both be precisely known. Instead, it settles into its lowest possible energy state, its ground state, which is not zero. This minimum energy, its zero-point energy, keeps the electron from collapsing and ensures atoms are stable. The very chair you're sitting on owes its existence to this fundamental quantum jitter. So, can we harness this limitless sea of energy? The idea of free energy from the vacuum is a sci-fi staple. The answer, unfortunately, is almost certainly no. To get useful work, you need an energy difference, a flow from high to low. Zero-point energy is, by definition, the lowest possible energy state. It's the bottom of the barrel. You can't extract energy from it because there's nowhere lower for the energy to go. The one terrifying exception would be if our universe exists in a false vacuum, a temporarily stable state with an even lower energy state possible. A transition to that true vacuum could release an immense amount of energy, but it would also likely rewrite the laws of physics and destroy our universe in the process. It's probably best we don't try to find out. From the stability of every atom to the accelerating expansion of the cosmos, the paradox of absolute zero teaches us a profound lesson. The universe isn't a static stage. At its most fundamental level, it's a dynamic, restless, energetic entity. Emptiness isn't empty. Stillness isn't still. Exploring paradoxes that shatter our perception of reality is what we love to do. These ideas challenge us and force us to see the universe in a new light. If you enjoy having your mind bent by the strange truths of physics and want to keep exploring the deepest questions about our existence, consider subscribing. We dive into a new mystery every week. So, the universe doesn't have an off switch. We set out on a quest for ultimate cold, for a state of perfect silence, only to find that such a state is a mirage. Instead, at the very edge of cold, reality becomes a shimmering, uncertain quantum hum, a symphony of possibilities conducted by the laws of quantum mechanics. It's a reminder that even in the most silent corners of the cosmos, there is a fundamental energy that can never be extinguished. The absolute zero paradox is more than a scientific curiosity, it's a philosophical revelation. It tells us that to exist is to vibrate. To be is to have energy. There is no true rest in this universe, only a ceaseless, underlying dance. The next time you experience a moment of profound stillness, remember the secret hum. Remember that you, and everything around you, are made of particles that can never truly stop, surfing forever on the restless waves of a quantum sea. It leaves us with a final, lingering question. If the baseline of reality isn't silence, but a constant, energetic hum, what other fundamental truths about our universe are we still hearing all wrong? The universe's ultimate tease you can never win. The universe, it seems, has a twisted sense of humor. It loves a good game. It sets the rules, lays out a cosmic playing field, and then dares us with the most tantalizing challenges you can imagine. It shows us the speed of light, an ultimate speed limit that we can get closer and closer to, but never actually reach. It hints at the moment of creation, the Big Bang, a point in time so dense and hot that our laws of physics just give up as we try to look at it. But maybe the greatest, most personal, and most frustrating challenge of all is a finish line it dangles right in front of us. A state of perfect, absolute calm that we can see, that we can understand, and that we can get infinitely close to, but are forbidden from ever crossing. This is the story of the universe's ultimate tease. It's a cosmic prank that says you can slow the frantic dance of every atom in existence down to a near total standstill, but you can never, ever make them stop completely. So what is this cosmic rule, this fundamental law of reality that feels like a practical joke? And why does it mean that true stillness, perfect quiet, is forever out of our reach? Let's unravel the third law of thermodynamics and begin the eternal chase for a state of rest that is forever, and tantalizingly, just beyond our grasp. The dance of the atoms. What is temperature, really? Before we can get our heads around the cosmic rule that forbids perfect stillness, we have to agree on what we're trying to stop in the first place. When we talk about temperature, what are we really talking about? For us, it's simple. We feel hot and cold. We put on a jacket in the winter and look for shade in the summer. Ice is cold, fire is hot. Got it. But what's happening on that hidden, microscopic level that creates these feelings? Imagine a huge ballroom, filled with thousands of dancers. When the music is fast and loud, the dancers are a blur of motion. They zip across the floor, they spin, they collide, they bounce off each other in a chaotic, high-energy frenzy. The whole room is humming with activity. This is what a hot substance looks like at the atomic level. The dancers, or atoms, and temperature, is just a measure of their average kinetic energy, how much they're moving. The hotter something is, the more violently its atoms are vibrating, spinning, and slamming into each other. Now, picture the DJ slowing the music way down. The tempo becomes a slow, lazy crawl. The dancers calm down. Their movements are less frantic, more sluggish. They just sort of glide across the floor with way less energy, and the collisions are just gentle bumps. The total energy in the ballroom has plummeted. This is cold. When you cool something down, you are literally pulling energy out of its atoms, forcing that frantic dance to become a slow, lazy shuffle. The different temperature scales we use, Celsius, Fahrenheit, are just different ways of marking the tempo of this atomic dance. But to really understand the asterisk limits of cold, we need a scale that gets to the heart of it all. We need the Kelvin scale. Unlike Celsius or Fahrenheit, which are based on something arbitrary like water freezing, the Kelvin scale is absolute. Its 0.0 Kelvin represents the theoretical point of no motion. This isn't just really cold. It's a concept so extreme it forces us to rethink what cold even means. 0 Kelvin, or absolute zero, is minus 273. 15 degrees Celsius, or minus 459, 67 degrees Fahrenheit. It's a temperature so low that, in theory, the atomic dance should stop completely. The dancers in our ballroom would freeze in place, mid-step, creating a perfectly still, silent picture. No vibration, no rotation, no movement at all. This is the finish line. This is the state of perfect stillness we're chasing. Seems simple enough, right? Just keep slowing down the music. Just keep pulling energy out until there's no energy left. The atoms will stop. But they won't. And the reason they won't is because the universe has a few more rules for this little game. Rules written into the very fabric of reality. To understand the ultimate tease, we have to first look at the other laws that set the stage. The cosmic rulebook, the first and second laws. Thermodynamics, the study of heat and energy, is built on laws that are as unbreakable as they come. They're often summarized with a cynical, but pretty accurate, bit of humor. The first law says, you can't win. The second law says, you can't break even. And the third law, the one we're wrestling with, says, you can't even quit the game. Let's quickly check the rulebook. The first law of thermodynamics is actually something you already know. Energy can't be created or destroyed. It just changes form or moves around. You can't get more energy out of a system than you put in. It's the universe's ultimate accounting principle. When we cool something down, we aren't destroying its heat. We're just moving that heat somewhere else. Your refrigerator doesn't make the heat inside it vanish. It uses a system to pump that heat out into your kitchen. That's why the back of your fridge is warm. It's a zero-sum game with energy. You can't win. But the second law of thermodynamics is where things get really interesting, and a little bit sad. The second law introduces a concept that is key to understanding, well, everything: entropy. What's entropy? Simply put, it's a measure of disorder, or randomness. Think about your bedroom. There's really only one way for it to be perfectly clean: every book on the shelf, every shirt in the closet. But there are millions, even billions, of ways for it to be messy. A sock on the floor, a book on the bed, a cup on the desk. The universe, if you leave it alone, naturally drifts towards these messier states, just because there are way more ways to be messy than to be neat. This universal slide towards chaos is what the second law describes. It says that in any closed-off system, the total entropy, the total disorder, will always increase over time. You can't break even. You always lose some useful energy to the chaos. Back to our atomic ballroom. When the atoms are hot and dancing wildly, they're in a high state of entropy. They can be arranged in a near infinite number of random ways. As we cool them down and their dance slows, we're forcing them into a more orderly state. We are fighting the natural tendency of the universe. We're trying to push the system's entropy down. The physicist Ludwig Boltzmann came up with a beautiful equation for this. He showed that entropy, which we call S, is related to the number of possible ways the atoms can be arranged, which we call microstates, or W. The equation is south equals K lane, W. K is just a constant. The important part is the link between S, entropy, and W, the number of arrangements. Lots of ways to arrange the atoms means high W and high entropy. Very few ways to arrange them means low W and low entropy. So, cooling something is a battle against the second law. It's an effort to reduce the number of possible arrangements for its atoms, to herd them from a chaotic frenzy into a disciplined formation. As we get colder and colder, we're lowering the entropy, getting closer and closer to perfect order. And this brings us right back to the finish line. If absolute zero is the point of zero motion, then it must also be the point of perfect order. A state where every atom is locked into one specific place in a perfect, rigid structure. In this ideal state, there is only one possible way to arrange the atoms. Just one microstate. W equals 1. And what happens to Boltzmann's equation when W equals 1? The natural logarithm of 1 is 0. Which means the entropy, S, is 0. This is the promise of absolute zero. A state of zero motion and zero entropy. The ultimate stillness. The perfect crystal. It's the logical end of our cooling process. It feels like it has to be achievable. And yet, it isn't. Because now, we finally come to the third and final rule in the cosmic game. The one that pulls the rug out from under us. The ultimate rule, the third law of thermodynamics. In the early years of the 20th century, the German chemist Walther Nernst was pioneering the new field of very low-temperature chemistry. He was working in a world of liquid air and strange new states of matter. As he studied how reactions behaved as things got colder, he noticed something profound. He saw that as temperatures plunged, the change in entropy during a reaction also plunged, and it looked like it was heading straight for zero as the temperature got closer to absolute zero. This idea, first called the Nernst heat theorem, was the seed that would grow into the third law of thermodynamics. It was later sharpened by Max Planck, who made a more powerful statement. The entropy of any pure, perfect crystalline substance approaches zero as the temperature approaches absolute zero. Let's break that down, because every word there matters. Pure means no foreign atoms messing things up. Perfect crystalline means the atoms are stacked in a flawless, repeating grid, like a perfect pyramid of oranges, with no mistakes. For a substance like that, as you cool it toward 0 Kelvin, its entropy, its disorder gets closer and closer to zero. This law does two incredible things. First, it gives us a universal starting point. It defines what zero on the entropy scale even means. But second, and more importantly for our story, it contains a hidden, almost cruel, twist. The law is often stated in a different, but equivalent way. It is impossible for any process, no matter how clever, to reduce the temperature of a system to absolute zero in a finite number of steps. This is it. This is the cosmic prank. The universe shows us the finish line 0 Kelvin, perfect order, perfect stillness, and then the third law states, clear as day, that we are forbidden from ever crossing it. You can't quit the game. You have to keep playing, forever chasing a goal you can never reach. But why? Why this rule that seems so arbitrary? Why can we get to 1/1,000,000th of a Kelvin, or 1/1,000,000th, but never to zero itself? The answer isn't a single wall we hit. It's buried in the very nature of cooling itself, a process that turns into an infinite, receding horizon. The eternal chase. Zeno's refrigerator. To get why absolute zero is unreachable, we have to think about the asterisk process of cooling. Remember, you don't create cold, you remove heat. You take energy out of a system, one step at a time. Imagine you have something that's already incredibly cold, say, 1 Kelvin. You want to make it colder. So you bring it into contact with something even colder, a cooling agent, and let a tiny bit of heat flow from your substance into the agent. Great. Your substance is now a little colder, maybe 0.5 Kelvin. You then recool your cooling agent to be even colder, and you do it again. Now your substance is at 0.25 Kelvin. Then 0.125 Kelvin. And so on. This is a simplified version of how real-world techniques like magnetic refrigeration work. But here's the trap, hidden in the math of the universe. With each step you take, the amount of heat you can actually remove gets smaller and smaller. The efficiency of your cooling process tanks as you get closer to absolute zero. Think of it like trying to wring water out of a damp towel. The first big squeeze gets a lot of water out. The next squeeze, which takes just as much effort, gets you less water. The one after that, even less. Eventually, you're putting in a huge amount of work to squeeze out one pathetic little drop. The process of cooling is exactly like this. The closer you get to zero, the more monumental the effort required to remove the next tiny fraction of energy. Your system becomes infinitely sensitive. Even a single stray photon bumping into your experiment can cause a huge jump in temperature. This creates a situation famously described by the ancient Greek philosopher Zeno. In one of his paradoxes, an arrow can never reach its target because first, it has to travel half the distance. Then it has to travel half of the asterisk remaining distance. And then half of that distance, and on, forever. The arrow has to cross an infinite number of halfway points, so, Zeno argued, it can never actually arrive. Cooling a substance to absolute zero is Zeno's paradox playing out in a real laboratory. To get to 0 Kelvin, you must first get to 0.1 K, then 0.01 K, then 0.001 K. You're forever getting closer, slicing the remaining distance by a fraction, but you never take a final step that lands you squarely on zero. You would need an infinite number of cooling steps to remove the very last bit of heat, and that's just not possible. It's not a technology problem, it's not that our refrigerators aren't good enough. The law says no process can do it in a finite number of steps. The finish line is an asymptote, a line that a curve approaches but never, ever touches. This is the first layer of the universe's great tease. But just when you think you've wrapped your head around the cruelty of the joke, you find out there's another, even weirder rule waiting for you at the bottom. Even if you could cheat, the universe has one last trick up its sleeve, thanks to the bizarre world of quantum mechanics. The quantum jitter. A universe that can't stand still. Let's just pretend for a second. Let's say we have a magic wand that lets us bypass the third law's infinite staircase and instantly zap a bunch of atoms to absolute zero. All thermal energy is gone. The atomic dance has stopped. We've done it. Perfect stillness. Or have we? This is where the universe pulls its final, mind-bending twist. According to quantum mechanics, even at absolute zero, the atoms would not be perfectly still. They would continue to jiggle, to vibrate with a tiny, irreducible amount of energy. This is called zero-point energy. This isn't some theoretical loophole. It's a direct result of one of the most fundamental rules in physics, the Heisenberg uncertainty principle. Werner Heisenberg discovered that you just can't know certain pairs of a particle's properties with perfect accuracy at the same time. The most famous pair is position and momentum. The more precisely you know a particle's location, the less precisely you can possibly know its momentum, and vice versa. Now think about what it would mean for an atom to be at a classical absolute zero. It would be perfectly still, so its momentum would be exactly zero. And since it's part of a crystal, it would be locked into a specific spot. We would know its position perfectly and its momentum perfectly. Heisenberg's uncertainty principle just screams, no. You can't do that. It's a flat-out violation of the rules of quantum reality. To avoid breaking this law, the atom must keep a tiny bit of motion. It has to jiggle in place, even in its lowest possible energy state. This minimum, non-zero energy is the zero-point energy. It's the energy that's left even when all the heat has been squeezed out. So, the universe has played its ultimate prank. The third law stops us from ever getting to absolute zero. And the uncertainty principle reveals that even if we could, the place we'd find wouldn't be the perfect stillness we were promised. It would be a place of quiet, but restless, quantum jitters. Nothing in the universe is ever truly, completely still. We actually see this strange behavior. Every element except one will freeze solid if you cool it down enough. The exception is helium. If you take helium and cool it all the way down toward absolute zero, it stays liquid. Its zero-point energy is so strong, its quantum jiggle so pronounced, that the atoms simply refuse to lock into a solid crystal. They slide past each other in a bizarre, frictionless, superfluid, a real-world glimpse of this quantum restlessness. The chase for absolute zero isn't a failure. It's a journey that has revealed some of the deepest truths about our reality, leading to incredible discoveries and new technologies we never could have imagined. The coldest places in the universe. Even though reaching absolute zero is impossible, the human drive to chase that finish line has led to some of the most extraordinary experiments ever designed. This isn't just a theoretical game. It's a real-life race to the bottom of the thermometer. So how cold have we gotten? In labs around the world, scientists have built machines that are, without question, the coldest places in the known universe. They use a mix of techniques, starting with things like liquid helium and then getting much more exotic. One of the most powerful tools is laser cooling. By firing precisely tuned lasers at a cloud of atoms, scientists can slow them down, like running into a relentless headwind of photons that saps all your energy. After that, they can use a final step called evaporative cooling. They hold the ultra-cold atoms in a magnetic trap and then slowly lower the walls of the trap. The hottest, most energetic atoms have just enough juice to escape, taking their energy with them. This lowers the average temperature of the atoms left behind. It's just like blowing on hot coffee. The fastest steam particles escape, leaving the rest of the liquid cooler. Using these techniques, we've achieved temperatures that are almost incomprehensibly cold. Not just millionths of a Kelvin, or billionths, but even trillionths of a Kelvin. As of 2021, the record for the coldest temperature was set by a team in Germany. They took a cloud of about 100,000 rubidium atoms and, using a sophisticated magnetic lens system inside a 120-meter drop tower to simulate zero gravity, cooled them to just 38 picokelvins. That is 38 trillionths of a degree above absolute zero. It's a temperature so close to the finish line that the difference is almost meaningless, yet it's still, fundamentally, not zero. The atoms were still jittering. The chase was still on. At these insane temperatures, matter starts to behave in ways that defy all intuition. When you cool certain atoms this cold, the quantum weirdness takes over completely. The atoms, now slowed to a near standstill, lose their individual identities. Their quantum wave functions spread out and overlap until the entire cloud of atoms acts like a single, coherent, superatom. This is the fifth state of matter, the Bose-Einstein condensate, or Beck, predicted by Satyendra Nath Bose and Albert Einstein in the 1920s and finally created in a lab in 1995. Seeing a Beck form is like watching the bizarre rules of the quantum world bubble up into our reality. It's one of the grand prizes we've won by playing the game, even though we know we can never claim the final trophy. And what about in nature? The coldest natural place we know of? For a long time, we thought it was the empty space between galaxies, which has a constant temperature of about 2.7 Kelvin from the faint afterglow of the Big Bang. But we've found one place that's even colder. About 5,000 light-years away lies the Boomerang Nebula. It's a dying star that's shedding its outer layers of gas incredibly fast, so fast that the rapid expansion is acting like a cosmic refrigerator. The Boomerang Nebula has been measured at a temperature of just 1 Kelvin. It is the only known natural object colder than the background radiation of space itself. And yet, even this spectacular wonder is still a full degree above the universe's ultimate limit. This eternal chase, this cosmic tease, reveals something profound about the universe and our place in it. We are constantly pushing against the fundamental limits of what's possible, and in doing so, we learn what reality is really made of. If you find these fundamental puzzles of the universe as fascinating as we do, make sure to subscribe and hit that bell icon. Every new discovery is another clue in the great cosmic detective story, and we'll be here to unpack it with you. So, where does that leave us? The universe has set up a game. A race to the bottom of temperature, a chase for the ghost of perfect stillness. The first law tells us the game is fair, energy is conserved. The second law tells us the game is rigged, disorder always wins in the end. And the third law tells us the game has no end. The finish line of absolute zero is an infinite horizon we can approach but never reach. And if that weren't enough, quantum mechanics chimes in at the very end to tell us that even if we could get there, the prize isn't what we thought it was. Perfect stillness is an illusion. The universe, at its most fundamental level, is a place of perpetual motion, of an unceasing, irreducible quantum jitter. The unattainability of absolute zero isn't a failure or a flaw. It's a fundamental truth. It teaches us that movement and energy aren't just properties of things in the universe. They're properties of the universe. The cosmos is not a static stage. It is a dynamic, evolving, and ceaselessly humming place. From the frantic dance of atoms in the heart of a star to the quiet, restless quiver of a crystal at a trillionth of a degree above absolute zero, everything moves. Everything jiggles. The ultimate tease is also the ultimate lesson. The game we can never win is the very thing that keeps the universe interesting. It forces us to be clever, to be curious, and to keep chasing. And in the eternal chase for a stillness that is forever out of reach, we discover the vibrant, chaotic, and beautiful nature of a universe that simply refuses to stand still. Physics just proved time is an illusion. What if I told you that this very moment, the present, might be an illusion? That the relentless ticking you feel, that sense of one second following another, isn't a fundamental part of the universe, but a trick of our own perception? It sounds like something out of science fiction, but this is the startling possibility that modern physics is beginning to explore. We are on the verge of a revolution in understanding, one that suggests time itself doesn't really exist in the way we've always pictured it. Instead, it might be an asterisk emergent property, a side effect of something even more basic: information. This isn't just about changing a definition. It could explain why, in order for our universe to have a past, present, and future, absolutely nothing in it can ever, truly, stand still. So, get ready to question what you thought you knew about the fabric of reality. Just take a moment and listen to the silence between your thoughts, the faint hum of the device you're watching this on, the distant sounds of life outside. In that stillness, you can almost feel it. A current. A flow. The unstoppable river of time, carrying you from the past, through this fleeting present, and into an unknown future. This feeling is one of a key aspect of our existence. It feels more real than almost anything. But physics, in its search for the ultimate truth, has stumbled upon a profound and deeply weird complication. The math, the observations, and the theories are all starting to point toward the same, unsettling idea. Time might not be real. And the journey to this idea didn't happen overnight. It started with one of the greatest minds in history taking apart our most basic beliefs, piece by piece. The anchor. Our shared experience of time. Before we get into the deep end of modern physics, let's start on common ground. Our shared, gut-level, and deeply personal experience of time. From the moment we're born, we learn to navigate its currents. We remember yesterday, we live in today, and we plan for tomorrow. This straight-line progression is the bedrock of our lives. We see it in the turning of the seasons, the slow crawl of the hands on a clock, the way everything around us grows and decays. It's the invisible thread that weaves together the story of our lives, giving it order, sequence, and meaning. This intuitive feeling was first written into the laws of science by Sir Isaac Newton. In his world, the world of classical mechanics that so perfectly describes our everyday reality, time was absolute. It was a single, universal clock. A master metronome for the entire cosmos. Newton saw time as a huge, invisible river, flowing at the exact same rate for every single person, planet, and galaxy, everywhere in the universe. It was the ultimate backdrop, the stage where the grand drama of existence played out. It didn't matter if you were on your couch, in a plane, or on the moon. According to Newton, the universe's clock ticked with the same, unwavering rhythm for all. This idea is incredibly powerful because it just feels right. It's what our senses tell us every day. When you watch a movie, you imagine the story unfolding frame by frame, one after another, in a fixed order. That's the Newtonian picture of the universe, a cosmic film reel playing out on the screen of reality. Our language is soaked in this idea. We spend time. We waste time. We run out of time, as if it's a currency that flows from a future vault into a past garbage bin. This classical view treats time as something totally separate from space. Space is the where, and time is the when. They're distinct and independent. You can move through space any way you want, forward, backward, left, right. But time? Time's a one-way street. You're a passenger, not the driver, carried forward without any control over your speed or direction. This feeling of being swept along is so powerful that for centuries, we never thought to question it. It was just a given. But in the early 20th century, a patent clerk in Switzerland, a young man who thought a lot about clocks and synchronization, started to see a crack in this perfect picture. His name was Albert Einstein, and his ideas were about to shatter our assumptions about the universe and set physics on the mind-bending path we're exploring today. He looked at that universal clock on the wall of the cosmos and realized, with a shock that would ripple through science for over a century, that not everyone's clock was ticking at the same speed. The crack in reality. Introducing the conflict. The first tremor that shook the foundations of Newtonian time came in 1905 with Einstein's theory of special relativity. The theory itself is built on two simple postulates, but their consequences are world-changing. One of those consequences is that time isn't absolute. It's relative. Specifically, the rate that time passes for you depends on how fast you're moving. Let's break that down. Imagine you have two perfectly synced atomic clocks. You keep one on Earth and put the other on a spaceship traveling at, say, 99% of the speed of light. For the astronaut on the ship, everything feels normal. Their heart beats regularly, their watch ticks once per second. But for you, watching from Earth, something amazing is happening. You'd see everything on board moving in slow motion. The astronauts' movements would be sluggish, and their clock would tick painfully slowly compared to yours. This isn't a trick or a mechanical glitch. Time itself is flowing slower for the astronaut. This leads to the famous twin paradox. Imagine one twin, Terra, stays on Earth. The other, Stella, goes on a round-trip journey to a nearby star at nearly the speed of light. When Stella gets back, she'll be much younger than her sister. For every year that passed for Stella, many more years might have passed for Terra. Stella has literally time traveled into Earth's future. This isn't just a thought experiment, it's a measurable reality. The effects of this time dilation are used every day in our GPS technology. Satellites are moving fast, so their onboard clocks tick a tiny bit slower than clocks on the ground. If engineers didn't correct for this, your GPS would be off by several miles a day. But special relativity was just the start. A decade later, Einstein gave us general relativity, which showed that speed isn't the only thing that can warp time. Gravity can, too. Einstein realized gravity isn't a force, but a curve in the fabric of spacetime caused by mass and energy. The stronger the gravity, the slower time flows. Time literally runs slower for someone at sea level than for someone on a mountaintop, because they're deeper in Earth's gravitational well. The difference is tiny, but it's real and has been measured. Near a black hole, the effect is extreme. A clock falling toward one would appear to slow down and freeze entirely at the event horizon. The implications are bizarre. If speed and gravity can change the rate of time, then there's no single, universal clock. Every observer has their own personal clock. Your now isn't the same as the now of an astronaut flying by, or an alien in another galaxy. This shattered the idea of a universal present and led physicists to a radical new picture: the block universe, or eternalism. In this view, if we can't agree on a single now, then maybe the only logical conclusion is that all moments past, present, and future are equally real. It's an interpretation, not a proven fact, but it's a direct consequence of relativity. Think of it like a reel of film. In the old view, we only experience one frame at a time. In the block universe view, the entire film reel already exists. The past isn't gone, and the future isn't unwritten. They're just different places in a four-dimensional block of spacetime. Our consciousness just experiences these frames in order, creating the illusion of time passing. Einstein himself was a firm believer in this. When his friend Michelson died, he wrote to the family, "Now he has departed from this strange world a little ahead of me. That means nothing." People like us, who believe in physics, know that the distinction between past, present, and future is only a stubbornly persistent illusion. But if time is just another dimension in a static block, then what about our powerful feeling of it flowing? Why does time seem to have an arrow pointing from past to future? To find the clues for that, we have to go even deeper into the strange world of quantum mechanics and information. The revelation, the emergent property of information. Einstein knocked down the first pillar of our understanding of time, its absolute nature. Now, physicists are taking aim at the second, its fundamental existence. The latest theories suggest time itself isn't a basic ingredient of reality at all. Instead, it's an asterisk emergent phenomenon. What does emergent mean? It's a property that doesn't exist in the individual parts of a system but arises from their interactions. Think about temperature. A single molecule of water doesn't have a temperature. Temperature is the average motion of many molecules bumping into each other. Or think about wetness. One H2O molecule isn't wet. Wetness is what you feel when trillions of water molecules interact with your skin. The new idea is that time is just like this. A single, frozen snapshot of the universe has no time. Time isn't a container that things move through. Instead, time emerges from the constant, dynamic change and interaction of everything in the universe. This is where information comes in, and it's the key. In physics, information isn't just data, it's fundamental. Every particle contains information about its state. Every time two particles interact, information is exchanged. According to this framework, this constant process of informational change is what creates time. The past is just the irreversible record of all the informational changes that have already happened. The future is the space of potential changes yet to come. And the present is that fleeting moment where potential becomes actual. Time, in this view, is the measure of this accumulating record of change. This idea also elegantly explains the arrow of time. The basic laws of physics actually work just as well forwards as they do backwards. So why do we only experience time one way? The answer lies in the second law of thermodynamics, which says that the total disorder, or entropy, of a system always tends to increase. An egg scrambles, but a scrambled egg never unscrambles itself. From an information perspective, this is a law about information spreading out. An intact egg has concentrated information. A scrambled egg has that same information dispersed and mixed up. The arrow of time is really just the arrow of increasing entropy, the irreversible spreading of information. Time flows forward because the universe's information is constantly getting more disordered and complex. Interestingly, some very recent theoretical work from 2025 suggests that in certain quantum systems, it might be possible for two opposing arrows of time to emerge, challenging even this picture. This brings us back to the main idea. If time is the record of informational change, then for time to exist, change must happen. For change to happen, things have to be in motion, vibrating, fluctuating, exchanging energy and information. A universe where everything was absolutely still would be a universe without change. Without change, no new information is recorded. In such a universe, the arrow of time would have nothing to point to. There'd be no before and after. In a truly frozen universe, time itself would have no meaning. So, the very existence of time is built on a cosmic rule. Nothing can ever truly stop. The constant dance of particles and fields isn't just happening in time. It's the very process that generates time. Time isn't ticking away on its own. It's being written, moment, by every single interaction in the cosmos. So what? The profound implications. Okay, so what if time emerges from information? This isn't just some abstract idea. It reframes our place in the cosmos. Let's go back to the frozen universe thought experiment. Imagine you press a cosmic pause button, stopping every single particle in the universe. Our old intuition says you've just frozen a moment in time. You could press play and time would resume. But if time is emergent, you wouldn't be pausing time. You'd be deleting it. A universe without change is a universe without time. It wouldn't be a frozen moment, it would be a state of existence entirely outside of time. A timeless, static, is, with no history and no future. The very act of seeing a frozen moment requires a consciousness that is itself changing, which our experiment forbids. This has staggering implications. Some physicists, like Stephen Wolfram, even propose that the universe is fundamentally a computational system. In his Wolfram Physics project, he suggests that reality emerges from simple rules being applied over and over to a vast network. In this view, space is the network's structure, and time is the computational process of the rules being applied. It's a controversial idea, not yet accepted by mainstream physics, but it's a fascinating way to think about it. This also connects to one of the biggest questions: free will. If the block universe model is correct, is our future already written? Is our sense of choice just an illusion as we walk a path that was always there? The emergent time theory offers a different angle. If time is generated by change, then the future isn't a fixed territory. Instead, it might be a cloud of probabilities. Quantum mechanics tells us that on the fundamental level, the universe isn't deterministic. Perhaps our choices are part of this process, collapsing probabilities into a single reality and adding new information to the cosmic record. The future isn't written, but it is constrained by the laws of physics. Ultimately, this whole framework suggests reality isn't made of things, but of relationships and interactions. An object's properties are defined by its interactions with everything else. This connects to speculative ideas that even gravity might be an emergent phenomenon tied to quantum information. The very force holding galaxies together might be a large-scale effect of quantum information dynamics. So, the next time you look at a rock, remember it's a lie. That rock is a whirlwind of activity atoms vibrating, pulling on you with gravity, participating in the great cosmic dance of information exchange that generates the very flow of time you experience. Its stillness is an illusion. Its existence, and yours, is defined by relentless, unstoppable motion. We started this journey on the familiar ground of time as a simple, flowing river. We saw how Einstein's theories broke that river into countless personal streams. And now, we find ourselves looking at a new ocean of understanding, where the river of time might dissolve entirely, revealing itself to be an illusion generated by the ceaseless hum of the universe's information engine. This idea that time is created by change and the accumulation of information is one of the most profound in all of science. It suggests that the universe, at its deepest level, may be timeless. And yet, from that timelessness, the dynamic reality we experience is born. This is the frontier of physics. The ideas we've talked about, from the block universe to emergent time and experimental hints from things like quantum dots, are active areas of intense research and debate, not settled facts. They're our best attempts to answer the biggest questions. What is time? Why does it have a direction? What is reality? The final answer might elude us for years, but the journey forces us to confront the limits of our intuition. The possibility that our experience of time is an illusion doesn't make our lives less meaningful. If anything, it makes them more wondrous. It suggests our existence is woven into the very process that writes reality into being. So, the next time you feel a moment slip away, becoming a memory, just pause. You may not be losing a piece of the past. You may be witnessing the universe in the very act of creating itself, painting a new frame onto the cosmic canvas. You aren't just a passenger on the river of time. You're a drop of water in the river itself. If this video bent your reality a little, and you want to explore more of the universe's deepest mysteries, make sure to subscribe and hit the notification bell. And for your next journey, check out our video on the block universe, where we dive even deeper into the idea that your past, present, and future might all exist right now. The universe is a perpetual motion machine. For as long as we've looked up at the stars, we've seen, well, stillness. A cosmic clockwork, vast and silent. We saw planets tracing their orbits and galaxies hanging like jewels on black velvet. So, we invented stories about this celestial order, about a universe in a delicate, eternal balance. We even came up with laws of physics that seemed to confirm it, a universe that, if left alone, would eventually run out of steam, pulled back together by gravity. For most of history, we believed the great cosmic story was one of an eventual, final rest. But we were wrong. Profoundly, beautifully, and terrifyingly wrong. In 1998, astronomers pointed their telescopes at the dying embers of distant stars and made a discovery that shattered our entire picture of reality. The universe isn't just expanding, it's speeding up. It's not coasting to a halt, it's flooring the accelerator. Something strange and unseen is pushing everything apart, a mysterious force that now dominates our cosmos. But the real shock, the mind-bending revelation, isn't just that the universe is in motion. It's that nothing in the universe can ever truly be still. Not for a fraction of a second. Not the largest galaxies hurtling through the void, and not the smallest particles that make up your own body. From the impossibly vast to the infinitesimally small, we live in a cosmos that is buzzing, vibrating, and expanding in every direction, all the time. We live inside a perpetual motion machine. And the quest to understand why reveals a fundamental, hidden truth about the very fabric of reality itself. The great deceleration that wasn't. To get the magnitude of what we discovered, you first have to understand what we expected to find. The story of our universe, as we understood it for most of the 20th century, was a cosmic battle between two immense forces, motion and gravity. In one corner, you have the Big Bang. Not an explosion in space, but an explosion of space itself. About 13.8 billion years ago, everything we can see was squeezed into a point so hot and dense it's hard to imagine. From that single moment, space began to unfurl, carrying the seeds of galaxies, stars, and planets along with it. This initial, explosive expansion is the great push, the momentum that sent everything flying apart. In the other corner, you have gravity. The patient, persistent force of attraction. Every speck of dust, every star, every galaxy, is constantly pulling on every other. Gravity is the universe's great decelerator. It's the cosmic brake pedal. And we thought, given enough time, gravity was destined to win the fight. This idea was so intuitive, so baked into our physics, that the only real debate was about how it would end. The fate of the universe came down to one crucial variable, its density. How much stuff was actually in it? If the universe was dense enough, gravity's pull would be overwhelming. The expansion would slow, halt, and then reverse. Galaxies would stop flying apart and start rushing towards each other, ending in a fiery apocalypse we called the Big Crunch, a mirror image of the universe's birth. If, on the other hand, the universe wasn't very dense, the expansion would continue forever. But it would be a tired, weary expansion, always slowing but never quite stopping. The universe would grow darker, colder, and emptier, fading into a state known as the Big Freeze, or the heat death of the universe. A third, Goldilocks, possibility existed on a knife's edge. If the density was exactly right, the expansion would slow down and approach a standstill, balancing perfectly forever. Notice what all three scenarios have in common. Whether it's a crunch or a freeze, the expansion is always slowing down. It had to be. Gravity demanded it. That was the central dogma of cosmology. The only question was how much. Even the great Albert Einstein, whose theories of general relativity are the bedrock of cosmology, believed in a static universe. When his own equations predicted that the universe had to be either expanding or contracting, he hated the idea so much he introduced a mathematical fudge factor to hold it still. He called it the cosmological constant, a kind of invisible energy in space itself that would perfectly counteract gravity. Later, after Edwin Hubble proved the universe was expanding, Einstein famously called the cosmological constant his biggest blunder. He'd missed the chance to predict the expanding universe from his own theory because he was so attached to the idea of a static cosmos. The irony is, as we're about to see, his blunder would turn out to be one of the most prophetic ideas in history. So, by the mid-1990s, the stage was set. The scientific community agreed. The universe was expanding, but it was slowing down. The great cosmic engine was running out of gas. The next step was just to measure that deceleration. To point our best telescopes at the heavens and find out which fate awaited us, fire or ice. Two independent teams of astronomers set out to do just that. They weren't looking for a revolution. They were looking for a number. A number that would tell us how fast the universe was slowing down. What they found instead would detonate the consensus. The discovery that broke physics. The year is 1998. Two rival teams are locked in a cosmological race. One is the Supernova Cosmology Project, led by Saul Perlmutter. The other is the High-Z Supernova Search Team, co-led by Brian Schmidt and Adam Rees. Their goal was to measure the universe's deceleration. To do this, they needed a special kind of cosmic yardstick. Something incredibly bright that could be seen across billions of light years, and crucially, something with a known, uniform brightness. Think of it like trying to gauge the distance to a row of streetlights. If you know all the bulbs have the same wattage, you can confidently say the dimmest lights are the furthest away. In cosmology, this is called a standard candle. By the 1990s, they had found the perfect one, a Type Ia supernova. A Type Ia supernova is the spectacular death of a white dwarf star, the dense remnant of a star like our Sun. It happens when a white dwarf is in a binary system, orbiting with a companion star. The white dwarf's immense gravity acts like a cosmic vampire, pulling material from its companion. Over millions of years, it siphons off mass until it hits a precise limit, known as the Chandrasekhar limit. At that exact point, the star's core triggers a runaway thermonuclear reaction. In seconds, the entire star is consumed in a cataclysmic explosion. For a few weeks, a single exploding star can outshine an entire galaxy of billions. And here's the beautiful part. Because every Type Ia supernova is triggered at the exact same mass, they all explode with almost the exact same intrinsic brightness. They are the perfect standard candles. By finding these supernovae in distant galaxies and measuring how bright they appear from Earth, astronomers could calculate their distance with stunning accuracy. But that's only half the puzzle. They also needed to know how fast these galaxies were moving away from us. This they measured using redshift. As the universe expands, it stretches the waves of light traveling through it. Light from distant, receding galaxies gets stretched to longer, redder wavelengths the farther the galaxy, the greater the redshift. By plotting a galaxy's distance from its supernova's brightness against its redshift, the teams could map the expansion of the universe at different points in its history. A supernova 1 billion light-years away tells you the expansion rate 1 billion years ago. A supernova 5 billion light-years away tells you the rate 5 billion years ago, and so on. The plan was simple. They assumed the expansion was slowing down. If that were true, it means the expansion was faster in the past. This means the most distant supernovae should actually appear brighter than expected for their redshift, because it wouldn't have taken as long for their light to reach us, making them closer and brighter than in a constantly expanding universe. The teams went to work. And slowly, the data points started to accumulate. And then came the moment of profound confusion. Adam Rees, analyzing the data, made a plot, expecting the points to fall along the curve for a slowing universe. They didn't. They were systematically off. The most distant supernovae weren't brighter than expected. They were dimmer. Consistently, stubbornly, inexplicably dimmer. This made no sense. If the supernovae were dimmer, it meant they were farther away than their redshift suggested. For them to be farther away, the expansion of the universe couldn't have been faster in the past. It must have been slower. And if it was slower in the past, that could only mean one thing. At some point, the universe had stopped slowing down and had begun to speed up. The result was so absurd their first reaction was that they'd messed up. As Brian Schmidt later recounted, his initial thought was, "I'm a failure. How am I going to tell everyone we've screwed this up?" They scoured their data for errors. Could some unknown intergalactic dust be making the supernovae appear dimmer? Could supernovae in the early universe have been different? They checked everything. Meanwhile, on the other side of the world, Saul Perlmutter's team was arriving at the exact same, unbelievable conclusion. When they presented their findings in 1998, the reaction was a mix of shock, excitement, and deep skepticism. It was like a biologist discovering that a ball, thrown into the air, had suddenly started rising faster and faster. It violated the most fundamental principle they had. Gravity pulls, it doesn't push. But over the years, the evidence became irrefutable. Other, independent lines of evidence from the afterglow of the Big Bang to the way galaxies cluster together all confirmed it. The discovery was real. Gravity was losing the battle. In 2011, Perlmutter, Schmidt, and Rees were awarded the Nobel Prize in Physics. They had set out to measure the brakes and had accidentally discovered the accelerator. The prime suspect. Dark energy. So, the universe is accelerating. It's a simple statement with staggering implications. If gravity isn't in the driver's seat, what is? If there's an accelerator, what's pushing it down? Scientists gave a name to this mysterious, anti-gravity force: dark energy. Energy, because it drives the expansion, and dark, because we have absolutely no idea what it is. It's completely invisible, detectable only through its relentless push on the fabric of spacetime itself. And this isn't some minor ingredient. When cosmologists did the math, the result was perhaps the most humbling discovery in human history. The atoms that make up you, me, the Earth, the Sun, and all the stars account for about 5% of the universe. Another 27% is dark matter, another mysterious substance that provides the gravitational scaffolding for galaxies but is also invisible. The rest of it, a staggering 68% of everything that exists, is dark energy. The dominant force in our cosmos, the primary driver of its future, is something we didn't even know existed a few decades ago. We're just foam on the surface of a vast, dark cosmic ocean. So, what is this stuff? The honest answer is, we don't know. But there are two primary suspects. The first, and simplest, is that dark energy is Einstein's biggest blunder, coming back to life. The cosmological constant. In this view, dark energy isn't a thing in the universe, but a fundamental property of space itself. It's the intrinsic energy of the vacuum. According to quantum mechanics, empty space isn't empty at all. It's a bubbling sea of virtual particles popping into and out of existence. This quantum fizz would exert a negative pressure, pushing spacetime apart. If dark energy is the cosmological constant, its density never changes. As the universe expands, the density of matter thins out, but the density of dark energy remains the same. In the early, smaller universe, matter was packed tighter and gravity was king. For the first 8 billion years or so, the expansion was, as expected, slowing down. But as space expanded, matter grew more dilute. Around 6 billion years ago, a tipping point was reached. The repulsive force of dark energy finally overtook the attractive pull of gravity. The brakes came off, the accelerator was pushed down, and the universe began the period of accelerating expansion we're in today. This model, known as lambda CDM, is the current standard model of cosmology. There is, however, a colossal problem. When physicists try to calculate how much this vacuum energy should be, they get a number that is 10 to the power of 120 times larger than what we observe. That's a 1 followed by 120 zeros. It's one of the worst theoretical predictions in the history of physics, and it suggests we're missing something huge. This leads to the second possibility, that dark energy isn't constant. Maybe it's a dynamic, evolving field that fills space, something nicknamed quintessence. Unlike the cosmological constant, its strength could change over time. If dark energy grows stronger, it could lead to a big rip, where the expansion becomes so powerful it tears apart galaxies, stars, and eventually atoms themselves. A new mystery, the Hubble tension. Just as scientists were getting comfortable with this new picture, another cosmic mystery emerged, one that pulls at the very threads of our standard model. It's a problem known as the Hubble tension. The Hubble tension is a persistent disagreement about a single number, the current expansion rate of the universe. The problem is that our two best methods for measuring it give two different answers. The first method looks at the early universe, by studying the cosmic microwave background, the afterglow of the Big Bang. Using our standard model, scientists can run the clock forward and predict what the expansion rate should be today. This method consistently gives a value of around 67 kilometers per second per megaparsec. The second method looks at the late universe, by measuring distances to nearby objects, using our trusty Type Ia supernovae and other standard candles. This more direct measurement consistently gives a higher value, around 73 kilometers per second per megaparsec. That might not sound like much, but the measurements have become so precise that the two values are now in a 5 sigma conflict. Statistically, this means there's only a 1 in 5 million chance the disagreement is a random fluke. Something is wrong. Either there's a subtle error in our measurements, or the model we're using to connect the early and late universe is incomplete. And just to stir the pot even more, some highly preliminary new research has been making waves. A 2025 study from a team at Yonsei University suggested that after reanalyzing supernova data, dark energy might actually be weakening, and the acceleration could be slowing down. Now, this is a very new claim and it faces intense scientific scrutiny. The consensus view remains that acceleration is ongoing. But this debate highlights that the story of cosmic expansion is far from over. The universe, it seems, is still full of surprises. The cosmic stage is set with motion, driven by a force that remains a complete enigma. But what if this grand, cosmic motion is only half the story? What if, to find the true heart of the universe's perpetual motion, we have to look in the opposite direction? Not out, to the farthest galaxies, but in, to the very fabric of reality itself. If you're finding this journey through the cosmos as fascinating as we are, take a moment to subscribe and join our community of explorers. We dive into the biggest questions in science every week, and we'd love for you to be part of the conversation. The second crime scene, the quantum realm. We've been on the largest possible scales, in a realm of galaxy clusters and cosmic horizons. Now, I want you to zoom in. Way in. Past the galaxies, past the stars, past the familiar world and into the building blocks of matter itself. Down past the molecules to the atoms. The quantum revolution of the 20th century revealed a world far stranger and more dynamic than we ever imagined. At this level, motion isn't just a possibility, it's a necessity. It's a non-negotiable rule of existence. To understand why, we have to meet one of the pillars of quantum mechanics, the Heisenberg uncertainty principle. Put simply, the uncertainty principle says you can't know certain pairs of a particle's properties with perfect precision at the same time. The most famous pair is position and momentum. The more precisely you know where a particle is, the less you know how fast it's going, and vice versa. This isn't a limit of our tools. It's an inherent fuzziness baked into reality. Now, think about what it would mean for a particle to be perfectly still. It would mean its momentum is exactly zero. But according to the uncertainty principle, if you know the momentum perfectly, its position must be infinitely uncertain. The particle would be everywhere in the universe at once. The bottom line is, a particle cannot have both a precise location and a momentum of zero. It cannot be perfectly still at a specific spot. This leads to the concept of zero-point energy. Because a particle can never be perfectly at rest, it must always have a minimum amount of vibrational energy. Even if you could cool something down to absolute zero, the coldest possible temperature, -273.15 Celsius, the particles within it would still be jiggling in their lowest possible energy state. This is the zero-point energy. Absolute zero is the point where all classical motion ceases, but you can never remove this fundamental quantum motion. In fact, this is one reason why reaching absolute zero is physically impossible. This isn't just theory. Zero-point energy is why liquid helium will never freeze solid at normal pressure, no matter how cold it gets. Its atoms' zero-point vibrations are just too energetic to let it lock into a solid crystal. The empty space of the vacuum is also subject to these quantum jitters. The vacuum is filled with quantum fluctuations, a sea of energy fields constantly oscillating. It's this vacuum energy that is our prime suspect for the dark energy that's accelerating the universe, though it's a suspect that comes with a massive catch. That 10 to the power of 120 problem we talked about. So now we have two scenes where perpetual motion is the law of the land. On the cosmic scale, galaxies are flying apart, pushed by the dark energy that might just be the zero-point energy of spacetime. And on the quantum scale, the very bits of matter are forever vibrating, unable to ever be truly still. Stillness, it seems, is an idea that has no place in the fundamental laws of our universe. Connecting the dots, the universe is a perpetual motion machine. So let's pull the camera back. We've uncovered a universe in a state of relentless, multi-scale motion. At the grandest scales, spacetime itself is expanding at an accelerating rate. At the most infinitesimal scales, particles are in a constant state of vibration, forever possessing a minimum quantum jiggle. The two great theories of modern physics, general relativity for the very large and quantum mechanics for the very small, both tell us the same thing. The universe is fundamentally dynamic. It's not a static stage, it's a process, a constant state of becoming. So why do we experience stillness? When you sit in a chair, you feel perfectly motionless. The ground beneath your feet feels stable. This feeling is a magnificent illusion, a trick of scale and biology. You don't feel the expansion of the universe because you and everything in our galaxy are being carried along with it. You don't feel the quantum vibrations in your chair because they are too tiny and too fast for your nervous system to register. Your sense of touch just averages out the frantic buzzing of trillions of atoms and calls it solid. Our brains evolved to navigate a human scale. We're masters of the middle ground, completely unequipped to perceive the universe as it truly is. A place of perpetual, unending motion. Stillness isn't a property of the universe, it's a feature of human perception. We began with a simple idea that the universe is a perpetual motion machine. And on every level we look, this appears to be true. Now, this isn't a perpetual motion machine in the classic sense. It's not breaking any laws of thermodynamics, and you can't harness it to power your city. It's a deeper kind of perpetual motion, woven into the very rules of reality. From the outward rush of galaxies to the inward dance of quantum particles, reality is a symphony of ceaseless movement. We've found a universe dominated by forces we are only just beginning to name, where 95% of everything is dark and unknown. A universe where our best theories lead to contradictions like the Hubble tension, hinting at even deeper physics yet to be discovered. The story of science isn't about finding final answers. It's about uncovering deeper and more profound questions. The discovery that the universe is accelerating didn't solve the mystery of our cosmic fate. It opened up a dozen new ones. We live in a cosmos that is more dynamic, more mysterious, and more magnificent than we ever imagined. The ground beneath our feet is not solid, and the sky above is not silent. We are all passengers on a tiny speck of dust, inside a machine of unimaginable scale and complexity, a machine that never, ever stops. And the journey to understand it has only just begun.